Have you ever wondered what secrets lie buried beneath your feet? What if I told you that every grain of sand, every rock formation, every mountain peak holds within it the most extraordinary story ever told? A story so epic, so mind-bending, that it makes every Hollywood blockbuster look like a gentle bedtime tale. Welcome, fellow time travelers, to the most incredible journey you'll ever take. We're about to embark on an adventure that spans not just centuries or millennia, but billions upon billions of years. This is the complete history of our planet Earth. And trust me when I say you've never heard anything quite like this before. But here's the thing that will absolutely blow your mind. What if I told you that Earth's entire 4.6 billion year history could be compressed into a single year? Imagine every catastrophic event, every evolutionary leap, every mass extinction packed into just 12 months. In this cosmic calendar, each month represents over 380 million years. Each day equals more than 12 million years of actual time. Every single second that ticks by represents 140 years of Earth's incredible story. Think about that for a moment. While you've been watching this video for just 30 seconds, we've already traveled through over 4,000 years of Earth's timeline. The entire recorded history of human civilization would flash by in less than a heartbeat. Now, before we dive headfirst into this cosmic adventure, I need you to do something for me. If you're ready to have your perception of time completely shattered, if you want to witness the most dramatic transformations our planet has ever experienced, then hit that like button and subscribe. Because what we're about to explore together will change how you see the world around you forever. Are you prepared to witness the birth of our planet from cosmic dust, to see oceans boil away and freeze solid, to watch entire continents dance across the globe like puzzle pieces, to witness the rise and fall of creatures so bizarre they seem pulled from the depths of imagination itself? Let's begin this magnificent journey into prehistory. Picture this scene. It's January 1st on our cosmic calendar, and we're about to witness the most violent birth in the solar system. But this isn't a gentle beginning. This is absolute chaos incarnate. The year begins with our planet as nothing more than a swirling mass of cosmic debris. Imagine a hellscape so intense that the very air would incinerate you instantly. The surface temperature soars beyond 2,000 degrees Celsius. That's hot enough to melt copper, hot enough to turn rock into flowing rivers of molten death. There's no oxygen anywhere to be found. The atmosphere is a toxic cocktail of methane, ammonia, and water vapor so dense it would crush you before the heat could finish the job. Volcanic eruptions tear through the planet's surface like angry wounds, spewing forth more poisonous gases into an already unbreathable atmosphere. This is what scientists call the Hadean Eon, named after Hades, the Greek underworld. And honestly, the name couldn't be more fitting. For the first few weeks of our cosmic year, Earth remains this ball of molten fury, completely hostile to anything resembling life. But here's where our story takes its first dramatic turn. On January 3rd, just 3 days into Earth's existence, something extraordinary happens. Something that will forever change the destiny of our planet. There's another celestial body sharing Earth's orbital path around the Sun. This Mars-sized object has a name, Theia. For cosmic ages, Earth and Theia have coexisted peacefully in their shared space around our young star. But on this fateful day, gravitational forces push Theia out of its stable position. What happens next is beyond catastrophic. Theia slams into Earth at an incomprehensible speed of 40,000 kilometers per hour. The impact is so violent, so earth-shattering, that it completely obliterates Theia and hurls billions of tons of material from both worlds into space. But from this cosmic destruction comes something beautiful. The debris from both planets, caught in Earth's gravitational embrace, slowly begins to coalesce. Over the following days, this scattered material forms into what will become our moon. This collision does more than just give us our natural satellite. Earth becomes more massive, its gravity stronger. The impact creates a larger planetary core that acts like a magnetic shield, protecting our world from the solar winds that could strip away our atmosphere. Without this cosmic accident, life as we know it could never have existed. Yet, the violence is far from over. For the next 3 months, Earth endures a relentless bombardment. Asteroids, comets, and meteorites pummel our planet from every direction. Not a single day passes without some cosmic projectile slamming into our world. Each impact releases tremendous energy, keeping the surface molten and hostile. But even in this apparent destruction, something remarkable is happening. The constant volcanic activity begins releasing gases that slowly form Earth's first atmosphere. It's not breathable by any stretch of the imagination, but it's the foundation upon which everything else will build. Then, on January 8th, something magical occurs. The water vapor in our primitive atmosphere finally cools enough to condense. For the first time in Earth's young history, it begins to rain. But this isn't a gentle spring shower. This is a deluge of biblical proportions. Torrential rainfall pounds the planet for over 100,000 years, dumping between 4 and 7 meters of precipitation. That's 10 times the rainfall of the most extreme tropical storms today. These primordial oceans fill every depression, every crater, every low-lying area on the planet's surface. For the first time, Earth has bodies of liquid water, but the cosmic bombardment continues, and these early oceans face a terrible fate. Watch what happens when a massive asteroid, tens of kilometers in diameter, slams into our young world. 5, 4, 3, 2, 1. The impact vaporizes the oceans instantly. All that precious water turned to steam in a fraction of a second. This cycle repeats endlessly. Oceans form, only to be vaporized by the next cosmic impact. Water condenses and falls as rain, only to be blasted back into vapor by asteroid strikes. It's a cosmic dance of creation and destruction that continues for millions of years. But gradually, as the solar system begins to settle, the bombardment slows. The oceans have more time to form and stabilize before the next devastating impact. Slowly, very slowly, Earth begins to cool. By the end of March, our planet has transformed dramatically. The lithosphere, made up of the crust and the rigid upper mantle, finally solidifies. Beneath it lies the asthenosphere, solid but elastic, capable of movement. This is the birth of plate tectonics, the process that will reshape our planet's surface for billions of years to come. The face of Earth is now outlined by oceans separating the first land masses. These proto-continents are small and scattered, nothing like the massive continents we know today. They're composed primarily of magmatic rocks rich in magnesium and iron. It's a harsh alien landscape of water and volcanic rock. As we reach the end of the first quarter of our cosmic year, representing nearly a quarter of Earth's entire existence, something seems impossible despite all this geological activity, despite the formation of oceans and the cooling of the crust. There's absolutely nothing to suggest that life could ever take hold here. The Earth's surface remains scorching hot. Cosmic impacts continue to strike regularly. The oceans still vaporize and reform in an endless cycle. This is a world that seems fundamentally hostile to any form of life. But March 3rd changes things. The oceans, which have appeared and disappeared countless times during the Hadean bombardment, finally achieve something resembling stability. Through continued precipitation and crustal solidification, ocean basins develop in a more permanent way. The Earth has finally cooled enough to maintain stable marine environments. Imagine a single drop of water falling from the moisture-laden sky, filling a small hollow in the rock, then another drop and another. Slowly, the water accumulates until a small pool forms. It's nothing like the vast oceans we know today, but there's something profoundly moving about this moment. Since January 1st, since the day Earth was born, nothing has seemed as peaceful and reassuring as the formation of this simple body of water. The violence of eruptions and the chaos of molten rock finally leaves room for something life-giving and essential. 24 hours pass on our cosmic calendar. While Earth was born on January 1st, something extraordinary finally appears on March 4th. Life. Life appears 3.8 billion years ago, though it's possible it emerged even earlier, perhaps during the late Hadean period. These first living organisms are bacteria that feed on sugars present in the primordial ocean. They're incredibly simple, single-celled creatures, but they represent the most important development in Earth's history. Nearly 3 months after our planet's birth, life evolves toward its first major innovation. On March 24th, we encounter a very special geological formation called stromatolites. Look closely at this shallow, stagnant water. This ocean basin serves as the cradle for the very first forms of microbial life. These are simple unicellular organisms, but life is here. It beats, it vibrates, it thrives. These cyanobacteria flourish in shallow waters, forming a kind of microbial carpet. They trap and bind sediment, creating distinctly layered fossilized structures that we can still find today. Over hundreds of millions of years, these tiny organisms will transform not only their immediate environment, but the entire Earth's atmosphere. What makes these living organisms so special is their ability to use photosynthesis to produce oxygen, an element that was previously unavailable on our planet. The first form of photosynthesis, called anoxygenic photosynthesis, doesn't actually produce oxygen as we know it. Instead, it releases elemental sulfur. The atmosphere at this time is completely devoid of free oxygen. But these anaerobic bacteria don't mind at all. They proliferate and develop as they please, provided the water isn't too deep. March turns to April, April to June. Bacteria continue to evolve, and 3 months later, they achieve something revolutionary. They successfully develop oxygenic photosynthesis. This time, they split water molecules and release oxygen into the atmosphere. They become the very first organisms capable of producing the gas that will eventually make complex life possible. It's time to pause and appreciate the magnitude of what's happening. We're at the beginning of June, almost 6 months into our cosmic year. Apart from these microbial life forms in the ocean, no other form of life has managed to establish itself on our planet. Seen from space, Earth shows stretches of water and a few stretches of emerged land resembling a rocky desert. The landscape appears chaotic and barren for thousands of miles. But our planet is about to undergo a major biological revolution. The emergence of oxygen-producing bacteria marks a crucial turning point in Earth's story. Oxygen begins accumulating in the atmosphere, and this seemingly simple change will have consequences beyond imagination. This oxygen accumulates to form what we know as the ozone layer. Ozone, made up of 3 oxygen atoms, forms an essential protective layer in the stratosphere about 20 kilometers above the surface. Though it represents only a tiny fraction of our atmosphere, this layer absorbs harmful ultraviolet rays that would otherwise sterilize the planet's surface. At the same time, Earth continues to experience significant geological activity. Plate tectonics reshape the surface while numerous impacts with celestial bodies continue to bombard our world. These phenomena shouldn't be seen as purely destructive. Despite their apparent violence, these forces promote the chemical alteration of Earth's crust. Since mid-March, we've witnessed the formation of banded iron formations, sedimentary rocks containing alternating layers of iron-rich minerals. It's the interaction between iron and oxygen in seawater that makes this formation possible. This process continues for hundreds of millions of years and intensifies dramatically as oxygen levels rise. The evolution of life is directly linked to this precise moment in our planet's history. Higher oxygen levels encourage the development of aerobic organisms, microorganisms that need oxygen to survive. This paves the way for the evolution of increasingly complex life forms. This is where everything changes. On June 14th, we're no longer dealing with simple single-celled life. Instead, we encounter new complex multicellular life forms called karyotes. The Proterozoic eon begins on June 14th, just after midnight, and will last several months until mid-November. During this critical period in our planet's history, climatic upheavals multiply dramatically. Earth will experience 3 major periods of intense glaciation. Shortly after celebrating the arrival of oxygen in the atmosphere and banded iron in the oceans, the first period of glaciation begins. Earth becomes entirely covered in ice. The oceans freeze solid, several kilometers thick. Seen from space, our planet is nothing more than a giant snowball. This is where we'll continue our journey next time, as Earth emerges from its frozen state and life prepares for its next great evolutionary leap. The story is just beginning, and the most extraordinary chapters lie ahead. On July 14th, Earth gradually emerges from its icy prison, shedding its frozen mantle like a snake discarding old skin. As the ice retreats, something remarkable begins to take shape on our planet's surface. The first major mountain formation event in Earth's history is about to unfold. This is the Hudsonian orogeny, and it's absolutely mind-blowing. An orogeny is essentially a mountain-building event that occurs when unstable portions of Earth's crust undergo massive contractions. Picture the planet's surface being squeezed like an accordion, forcing rock formations to buckle and rise into towering peaks. The Hudsonian orogeny becomes the most significant mountain-building event of its time. It creates what we now know as the Precambrian Canadian Shield and forms the geological foundation of the North American continent. This isn't just a few hills popping up here and there. We're talking about the birth of an entire continental core, a zone of magmatic rock formed through the cooling and solidification of molten material deep within the Earth. But Earth isn't finished with its geological theatrics. Around September 20th, a second massive mountain-building event takes place. The Grenvillian orogeny explodes into action, and this one is associated with something truly spectacular: the construction of the supercontinent Rodinia. Think about this for a moment. We're witnessing the assembly of one of the most important supercontinents in Earth's history. Massive land masses are slowly drifting across the planet's surface, colliding with tremendous force, welding themselves together into a single colossal continent. The Grenvillian orogeny is one of the two most important mountain-building events our planet has ever experienced. The second major orogeny, the Pan-African, takes place around November 1st, occurring between two periods of devastating glaciation. So let's step back and appreciate what the Proterozoic has delivered so far. 3 periods of intense glaciation that turn our planet into a frozen wasteland. 3 massive mountain-building events that reshape entire continents. And 3 supercontinent formations: Columbia in August, Rodinia at the end of September, and Panotia in mid-November. The last few months have been absolutely intense in both climatic and geological terms. But while all this dramatic reshaping is happening on the surface, there's been incredible movement in the living world as well. And it's time we take a much closer look at these evolutionary breakthroughs. We're already approaching the end of August, with just 4 months of cosmic time left to explore. While Earth welcomed its first living organisms back in March, it took another 5 months for life to evolve in truly significant ways. Shortly after the first major mountain-building event, between devastating meteorite impacts, eukaryotes achieved something revolutionary. They developed the ability to undergo mitosis. This might sound like scientific jargon, but this is actually a monumental leap forward. A mother cell can now divide into 2 daughter cells that are genetically identical to the original. This is cellular reproduction at its most fundamental level. But that's far from the only breakthrough happening. Just days later, around September 1st, scientists believe something called endosymbiosis begins to occur. This is where things get really fascinating. If this theory is correct, then a host cell engulfs photosynthetic cyanobacteria, forming the very first symbiotic relationship in our planet's history. Imagine one organism literally swallowing another, but instead of digesting it, they form a partnership. The larger cell provides protection and nutrients, while the smaller organism provides energy through photosynthesis. This isn't just cooperation. This is the birth of a completely new type of life form. During October, eukaryotes become capable of using an entirely new multiplication process called meiosis. It takes almost 4 weeks for this phenomenon to develop, but the implications are staggering. Unlike mitosis, which creates identical copies, meiosis creates 4 cells with distinct genetic identities. This is the foundation of sexual reproduction and genetic diversity. Without this development, complex life as we know it could never have existed. Scientists have discovered numerous microfossils dating from this period, though unfortunately, many remain unclassifiable. Time has taken its toll, and we can't make their testimony completely clear. However, we know they were eukaryotes, and they were large organisms with shells made of chitin, a tough, flexible organic substance that forms the protective covering of insects and other arthropods today. These microorganisms had appendages of various shapes and sizes, and scientists believe they were an important part of the ocean's plankton community. They shared the seas with new living beings that were completely different from the first bacteria we encountered earlier in our journey. The ability to create different types of cells opens up an incredibly wide range of possibilities for living organisms. Life forms begin adapting to different environmental conditions with remarkable speed and creativity. We reach November 13th, and something extraordinary appears in our timeline. The Ediacara biota emerge, representing what we might call the first true animals. We can observe Namacalathus here, an animal with a calcified skeleton. This creature is one of the living organisms that benefited tremendously from the oxygen production that now accumulates in both the atmosphere and the oceans. Namacalathus serves as one of the rare witnesses to this crucial period. Most of its contemporaries had soft bodies that didn't fossilize well, but we can find traces of their existence in sediments, giving us glimpses of their presence and shape. Creatures like Sprigina, Dickinsonia, and Tribrachidium left their marks in the geological record. We also encounter Charnia, which resembles a plant but is actually an animal. It's shaped like a feather and lies firmly attached to the seabed, filtering water and feeding on microorganisms, more commonly known as plankton. Major developments occur in algae during this time as well. Green algae diversify significantly, promoting the eventual transition of plants from aquatic to terrestrial environments. Red algae and brown algae also contribute to the diversity of the very first marine ecosystems. The Proterozoic chapter closes with wonderful news for the living world. In addition to major climatic, environmental, and geological changes, this eon establishes the foundation for a future explosion of marine life. It represents the transition from simple, single-celled life to complex, multicellular organisms. Geologically speaking, terrestrial activity remains incredibly intense. The various mountain-building events and continental movements show us that Earth is dynamic, in perpetual change, and there are bound to be dramatic events arising from this vigorous internal activity. We're now approaching the end of our cosmic year. Earth's entire existence from birth to the present day is drawing toward its conclusion, yet there's still so much to discover. Today is November 17th, and only 44 days separate us from the emergence of the first multicellular animals to the present day. There will be a distinct before and after November 17th. This date represents something incredibly special for our planet. In fact, it's one of the most significant events in our entire history. We've just experienced almost 10 months on Earth. These 10 months represent the Precambrian supereon, which includes the Hadean during the first weeks of life, then the Archean, and finally the Proterozoic. Between November 17th and 21st, we enter the Cambrian period, the very first era of the Phanerozoic eon. New groups of animals multiply to such an extent that scientists describe it as an explosion of life. The Cambrian changes the entire order of life forever. The emblematic animal of this period is the trilobite. Unlike previous animals which lack diversity and remain very simple, we can see that life evolves dramatically just by examining this marine specimen. The invention of shells and protective coverings not only facilitates fossilization, helping us find these precious witnesses to the past, but represents a major breakthrough in marine diversification. At last, we can begin talking about true ecosystems and distinct biological communities. The seabed becomes home to numerous arthropods, including trilobites. Crustaceans and chelicerates can be observed throughout the ocean, along with members of the mollusk families such as gastropods and brachiopods. We're still far from the seascapes we recognize today, but it's amazing how much life seems to flourish during this time. We encounter Opabinia, Wiwaxia, Marella, and even Pikaia. The latter looks somewhat like a small marine centipede, easily navigating around the seabed which teems with life. We can also observe some truly bizarre creatures such as Hallucigenia with its peculiar spines and Anomalocaris. But all of these creatures, including the trilobites, should be wary of approaching predators like Anomalocaris. As in any ecosystem, predator-prey relationships become established. The very first true ecosystem on Earth follows this fundamental rule of nature. While many of the animals we've mentioned are suspension feeders or filter feeders, Anomalocaris represents something revolutionary, the very first predator in the history of life. Its evolution is remarkable. It possesses compound eyes like modern flies, with up to 16,000 individual facets. It also has a mouth, teeth, legs, fins, and even a long tail. This is dramatically different from the single-celled organisms or basic microorganisms we encountered before the Cambrian period. Here we witness the emergence of specialized organs with specific functions. The evolution and diversification of living organisms is truly underway. While everything seems possible in the ocean from this point forward, the situation on the surface tells a different story. The landscape appears quite different and rather desolate. On land, everything seems limited to rock and dust. Although the ozone layer is thickening, it remains too thin to truly protect the continental surfaces. Without adequate protection, ultraviolet rays easily destroy any life forms that might have the courage to establish themselves on land. There isn't the slightest plant cover for miles around. Without this protective green carpet, the continents remain in poor condition, with intense erosion affecting vast areas. On the continent of Gondwana, you can observe how arid and desert-like the entire region appears. We're entering a new era, and during these 4 short days, Earth will experience incredibly intense geological activity. While the northern hemisphere remains completely devoid of land masses, the southern hemisphere hosts the impressive continent of Gondwana, which includes what will become South America, Africa, India, Australia, and Antarctica. Further away in the tropics, we can also observe three other continents: Laurentia, Siberia, and Baltica. These continental masses aren't static. They move constantly, changing the arrangement of land and sea hour by hour. They trigger the opening of new ocean basins to the south and the beginning of the closure of others. This plate movement undoubtedly includes phenomena that have major impacts on living organisms. The activity of oceanic ridges, for example, causes the oceans to overflow onto continental shelves. Minute by minute, sea levels rise. They're now 200 meters higher than today's levels. Perhaps this elevation enables plants like Marchantia polymorpha to finally establish themselves on land. Until now, life has been exclusively marine. We're still far from having rich and diverse ecosystems on the continents, but the arrival of this liverwort plant on solid ground gives us tremendous hope for the future. Back in the ocean, during this short 4-day period at the end of November, life has time to regain its strength and diversify once again. On November 24th, a wealth of marine life can be observed blooming across the globe. Our magnificent journey through Earth's prehistoric timeline continues to unfold, revealing secrets that will forever change how you perceive the world beneath your feet. Right in front of you, in this part of the ocean, swims a magnificent creature called Proterozoic, an orthocone cephalopod mollusk that dominates these ancient waters. At 30 centimeters long, this specimen might seem modest, but it's far less impressive than one of its relatives, Camarasaurus, which reaches an astounding 10 meters in length. If the Cambrian period is associated with trilobites, then the animal that truly epitomizes the Ordovician is undoubtedly the orthocone. In the large predator category, we must also mention Megalograptus, a eurypterid also known as a sea scorpion. Measuring around 80 centimeters long, it attacks trilobites, probably targeting species like Isotalus. These ancient arthropods are in increasing decline as new predators emerge. Other animal groups, however, are diversifying and expanding dramatically. Here we encounter members of the conodont family, and just meters away, we observe nautiloid cephalopods taking full advantage of the resources and shelter provided by bryozoan sponges, solitary corals that resemble sea anemones, and crinoids that look like colorful underwater forests. The richness of marine biodiversity has developed at an absolutely staggering pace. The number of families has tripled, and the number of genera has quadrupled, according to detailed paleobiological data. This database represents a compilation of information on over 30,000 fossils and remains a benchmark for studying ancient biodiversity worldwide. Let's examine the geological and climatic conditions affecting our marine animals. The drop in surface water temperature may have actually favored this marine richness. We've witnessed temperatures fall from 4 to 5 degrees Celsius to 30 degrees Celsius, an enormous difference that inevitably impacts aquatic life. Phytoplankton and bottom-dwelling algae are the first to benefit from this temperature shift. Animals dependent on these primary organisms also benefit through a domino effect. The multiplication at the base of the food chain enables filter feeders, grazers, and other primary consumers to develop and diversify. Naturally, predators aren't far behind in taking advantage of these new opportunities. On land, although everything remains fragile, an incredible event is taking place. The conquest of the continent by living organisms begins in earnest. For now, it's just small mosses settling at the water's edge. This time on land, it's not merely rocks, sediments, and minerals, but actual life forms beating a path forward. Marchantia polymorpha represents one of the first plants to settle on solid ground and anchor itself in soil, accompanied by various mosses and liverworts. The expansion of terrestrial plants triggers an acceleration in the chemical erosion of volcanic rocks on the continents, which reduces carbon dioxide concentration in the atmosphere. The weathering of continental rocks also releases massive quantities of phosphorus, which rivers transport to the oceans. What does this mean for marine fauna? Everything. This enrichment favors the development of phytoplankton, increases photosynthesis, and enables countless species to develop and diversify. This new nutrient source enriches marine environments, enabling the development of entirely new ecological niches. If everything seemed promising for marine fauna and flora, and if all appeared possible for terrestrial organisms, that optimism doesn't account for the first catastrophe about to unfold. On November 24th, for several minutes now, an ice age has been brewing. It will soon eliminate a quarter of all marine animal families and half of all marine animal genera. This represents the second biggest extinction event in Earth's history. Increased photosynthesis lies at the root of atmospheric carbon dioxide depletion. This undoubtedly triggers the famous glaciation responsible for the biological crisis that follows. For the first time, life must recover from a biological crisis on a massive scale. Nature will need to adapt to this cycle of renewal, and it won't be the last time it experiences such devastation. November 25th arrives, and we enter the Silurian period. With it, flora and fauna must once again flourish. It takes several hours to achieve this recovery, thousands of years in actual time, but Earth possesses remarkable resilience and doesn't surrender easily. The generalized warm climate allows coral reefs populated by tetracorals and tabulates to dominate the edges of ancient ocean basins. On shallow seabeds, the melting of polar ice caps causes a general rise in sea levels, and shallow seas now cover vast continental shelves. Speaking of continental shelves, there's a major geological event worth noting. Do you notice these mountains? They are evidence of the slow formation of the Caledonian orogeny, another massive mountain-building event reshaping our planet's surface. Let's dive back into the ocean and observe how life returns to normal. Crinoids reign supreme during the Silurian. Here we see eucalyptocrinites, which can reach 2.5 meters in height. The Silurian also witnesses the emergence of entirely new groups. A few days ago during the Ordovician, agnathons or jawless fish appeared, but it's during the Silurian that they experience a real evolutionary explosion. The group now includes arandaspids, heterostracans, osteostracans, and thelodonts. A few minutes later, nothostomes, the jawed vertebrates, make their appearance. This represents a new evolutionary turning point for fish. Climatius reticulatus stands as one of the very first jawed vertebrates on our planet, swimming through the world's waters. Other fish even display their first mobile scales. Not far away, we observe eurypterids attacking emblematic predators of the previous period, giant orthoceratids, dethroning them from their position as apex predators. But in just a few hours, they'll face something much more formidable. Placoderms, or armored fish, begin dominating Silurian ecosystems. Giant forms like Dunkleosteus emerge as fearsome predators that will overwhelm eurypterids, even the largest specimens. Life flourishes for many other groups of marine animals, including brachiopods, mollusks, and graptolites. If changes prove significant in the water, it's at the surface where they become most impressive. Until now, Earth, impoverished by erosion and ultraviolet radiation, presented only a barren, arid, almost chaotic landscape where no plants managed to take root. But on November 26th, everything appears different on Earth. Hope emerges at the water's edge. Not only algae, but also vascular plants have emerged from the water. Life gradually returns to the continent. It's through Cooksonia that the first riverside and seaside vegetation takes root. The arrival of this plant leads to the creation of a small ecosystem. It's still in its infancy and remains fragile, but it's incredibly promising. From second to second, it grows, develops, and takes on real significance. Take a careful look at the ground. An inhabitant has already found a home in this little corner of vegetation. You can observe the first scorpion capable of taking steps on land, Palaeophonus. But there are also spiders and terrestrial myriapods like this millipede, Pneumodesmus. One of the most interesting features of its anatomy is the presence of spiracles, tracheal openings that allow air breathing. This creature represents one of the very first living beings capable of walking on Earth. Until now, almost no other creature possessed this ability. In water, life operates differently. Here, you must support your own weight against air pressure, breathe differently, and move without the assistance of water buoyancy. The animals you've just witnessed are the first to achieve this remarkable feat on our planet. An ending always signals a new beginning. In the space of just a few hours, at most a few days, drastic changes occur, and new processes set themselves in motion. In geological terms, the Devonian period witnesses the end of the Caledonian orogeny, but also the beginning of the Hirsanian orogeny. For animals, the few hours separating November 28th and December 1st mark the end of several lineages. Osteostracan placoderms, pelagic graptolites, and eurypterids gradually disappear. During this period, ecological niches become vacant, allowing other species to fill the void. New groups appear just hours later. Lungfish, the impressive acanthodians, elasmobranchs, osteolepiform fish, and coelacanths make their entry into the aquatic world. The marine environment becomes more active than it was just days ago. The animals differ significantly from those we've encountered previously. Large hunting animals make their appearance, such as this Dunkleosteus attacking a shark ancestor. Other predators remain more modest in size, such as Carolepis, which attacks schools of acanthodians. Among fish, we observe significant diversification. Actinopterygians, or ray-finned fish like Chirolepis, increasingly populate the world's oceans. Another important group also establishes itself on the seabed. Sarcopterygians, or lobe-finned fish, appear alongside chondrichthyans, such as primitive shark ancestors. The ocean's architects continue building masterpieces. Stromatoporoids, tabulate corals, and rugose corals construct increasingly elaborate coral reefs. These reefs house hundreds of different species, including various brachiopods and goniotites, coiled cephalopod mollusks. On land, the landscape has never appeared so peaceful and reassuring. Vegetation, albeit small with most plants around 10 centimeters tall, covers increasingly large areas of the surface. A genuine vegetation cover begins taking shape. If you observe carefully, you'll notice that in several places, one plant grows taller than the others. It displays a more intense green coloration. This is a lycopsid called Aster oxylon, measuring around 50 centimeters in height. But it's not alone. Let's extend our investigations further and head toward the Appalachian Mountains. Here, the temperature hovers around 28 degrees Celsius and humidity remains very high. This represents one of the oldest forests in the world. It's extraordinary to finally witness such a landscape taking shape before our eyes. Like modern forests, it operates in distinct stages. At the water's edge, you observe the smallest plants such as Lycopsid drepanophycus. A little further inland grow bushy, scaly shrubs called Xylophyton. Then Tetraxylopterus appears along the forest edge. There are herbaceous lycopsids throughout, but above all, tree lycopsids dominate the landscape. These represent the very first trees in the world. The tallest specimens are undoubtedly Pseudosporochnus, reaching approximately 8 meters in height. They resemble palm trees in many ways. It's hardly surprising that new ecological niches open with the advent of such extensive plant cover. Creatures like Pneumodesmus occupy these areas, but most significantly, the first tetrapods emerge. It's now December 1st at 1 a.m., and we're witnessing the birth of Acanthostega, the first aquatic tetrapod. A few hours later, around 3 p.m., one of the oldest tetrapods, the famous Ichthyostega, also appears on our beautiful blue planet. Ichthyostega preserves characteristics of a fish with its caudal fin tail and ventral surface covered with small scales, but it also possesses the first true tetrapod limbs with 3 joints: hip, knee, and ankle. The reason it's so famous is undoubtedly that it represents one of the very first aquatic vertebrates to attempt an adventure on the continent. It's equally adapted to swimming and to locomotion on land. Despite this encouraging news for terrestrial life, likely caused by oxygen depletion in the oceans, a new mass extinction rages across our planet, causing the loss of almost 75% of all species. December 2nd arrives, and we enter a new period, the Carboniferous. The collision of European, American, and Gondwanan plates continues the formation of the Hercynian mountain chain, welding almost all continental masses into a single supercontinent called Pangaea in just a few hours. The intense erosion accompanying the formation of the Hercynian chain, coupled with lush vegetation from coal forests, continues driving down atmospheric carbon dioxide levels and consequently the planet's temperature. Land masses at the South Pole become covered with ice. Are we facing a new biological crisis? For now, let's return to December the 2nd. In the space of a few hours, the huge temperature variation between the poles and the equator causes a zonation of vegetation. Equatorial zones become covered by large coal forests featuring lepidodendron, calamites, and chordates. In temperate zones, deciduous trees such as Glossopteris gradually take over. In swamps, a wide variety of other plants provide new ecological niches. Neuropteris, for example, thrives in this explosion of seed plants. As reproduction becomes easier, the development of these plants extends over ever wider territories. Vegetation cover becomes more diversified and denser. This great diversification of vegetation encourages the expansion of diverse and luxuriant terrestrial fauna. On December 3rd, amphibians such as Eriops take up residence in the marshes. Insects become abundant as well. There are centipedes, spiders, scorpions, but also the first flying insects such as Stenodictia, a giant version of the dragonfly called Meganeura. Other giant versions of insects appear in early December alongside this dragonfly with a wingspan of almost 70 centimeters. Arthropleura represents a centipede measuring 1.5 meters long. It's absolutely gigantic. According to scientists, there's an explanation for these disproportionate sizes found in many insects of this time period: high oxygen levels. Indeed, during the Carboniferous era, a particular event favors this significant size increase. The Carboniferous era takes its name from coal formation. The great trees we've observed collapse into wet soils, creating carbon deposits that become our main coal reserves millions of years later. But for now, as carbon becomes buried in the soil, oxygen levels in the atmosphere increase by 15 to 25% more than present levels. Insects benefit tremendously from this oxygen influx. Another major event occurs with the arrival of the amniotic egg. If this provides new impetus for species emergence, it's not the only significant development of the period. On December 5th, synapsids appear. A few minutes later, they diversify, adding new groups and species. Diapsids soon follow suit. By midday on December 6th, the two great clades of synapsids and diapsids are already perfectly established. Hylonomus, one of the first diapsids, appears just seconds later. Archaeothyres also emerges, representing the oldest known diapsid that will undoubtedly give rise to the great clades we recognize today: crocodiles, dinosaurs, and the birds that descend from them. We can also observe Archaeothyres, the oldest synapsid that gave rise to the mammalian lineage. The Permian period brings the Carboniferous to an end, along with the coal formation so characteristic of the previous era. During this new period, lasting just a few days, a fungus appears that makes all the difference. It becomes capable of degrading wood, or at least the lignin composing it. This development puts an end to coal formation. While this fungus marks a real division between the two eras, certain continuities persist. Pangaea, for example, has now reached almost its climax. The continents of Gondwana and Laurasia appear virtually unified. The synapsids we encountered just hours ago now represent the main dominance of their ecosystems, as exemplified by the carnivorous Lycanops of the Gorgonopsian family. Amphibians despite their dominant role in previous eras as the first vertebrates to embark on partially terrestrial life, increasingly give way to these synapsids and also to anapsids. Prehistorics represent large anapsid reptiles adapted to swamp life like today's hippopotamuses. Their limbs remain stocky and erect, and their bodies feature dermal armor, their herbivores reaching up to 3 meters in length. Until now, no land animal had truly adopted this herbivorous diet, but gradually, synapsids welcomed their first vegetarians. The first bipedal animals appear as well. This mode of movement enables them to gain agility and speed. Others attempt to fly or at least glide initially. However, there's no shortage of predators in these environments. We've observed that Lycaenops represents a fierce predator, but it's far from alone. A few archosaurs make timid appearances, but synapsids remain by far the dominant vertebrates of this period. Trees remain very much in evidence, some reaching enormous sizes and offering excellent ecological niches, where insects and small reptiles flourish. Other genera, such as cycads, palm-like plants, enrich the ecosystem of Permian forests. In spite of all this diversification, a major biological crisis strikes Earth. Until now, life seemed well underway and following its natural course. One evolution followed another. Major diversification processes were occurring, and marine and terrestrial ecosystems were flourishing. But on December 11th, intense activity and brutal events upset the established order. For more than 1 hour, equivalent to almost 500,000 years, one volcanic eruption follows another. They form a layer of lava, 6 kilometers thick. Just imagine, 6 kilometers of molten rock. The amount of gas produced is phenomenal. Temperatures soar above 40 degrees Celsius, while oxygen levels plummet dramatically. 75% of terrestrial species and 95% of marine species eventually disappear. This event is sometimes described as the mother of all extinctions. Earth has already experienced its 4th major extinction, but this one proves undoubtedly the most severe and intense of all. 95% of species have been wiped from the map. The cycle of life seems completely annihilated. Asteroid impacts and intense volcanic activity appear to be the causes of this exceptional biological crisis. The Permian period, like the entire Paleozoic supereon, closes on this tragic note. Yet another major biological crisis strikes our planet. But like any period of crisis, new diversification follows, with the birth of new species and significant evolutionary radiation. In short, life begins again, and our incredible journey through Earth's magnificent prehistory continues to unfold with even more dramatic chapters ahead. During the Paleozoic periods, we witnessed events unfolding in rapid succession. Each era lasted just a few days on our cosmic calendar, yet geologically, climatically, and biologically, the transformations were absolutely enormous. But from the Mesozoic onward, everything accelerates even further. The pace becomes intense, with evolutionary radiations and biological developments multiplying at breakneck speed. Everything seems in constant turmoil without ever running out of steam. December 11th marks a pivotal moment. In the aftermath of the greatest biological crisis our planet has ever witnessed, flora and fauna begin regaining a certain vitality. Life returns, but not for long. the Triassic becomes the only period in Earth's history to begin and end with mass biological extinctions. It takes several minutes for our planet to catch its breath. On the whole, plants survived the crisis rather well. The lycopsids and sphenopsids we encountered earlier, along with ginkgos and the famous Glossopteris, remain present. Such flora undoubtedly facilitates the return and diversification of animal life. Little by little, vegetation in the northern hemisphere takes on a completely new appearance. Conifers become more numerous and diversified, like these early gymnosperms spreading across the landscape. Among animals, we observe some groups being stripped of their dominance, while others step in to fill the vacant ecological spaces. Until now, amphibians have occupied significant territory, and synapsids have been fairly well established. But diapsid reptiles are gradually conquering the continent. The famous archosaurs, which had been very timid and few in number during previous eras, take full advantage of this biological crisis to fill empty ecological niches. A few minutes after midnight on December 12th, archosaurs experience an exceptional evolutionary radiation. They will later give rise to several lineages including crocodiles, dinosaurs, and pterosaurs. During the Triassic period, crocodilomorphs such as Desmatosuchus and dinosauromorphs such as Lagosuchus, Saltopus, and Marasuchus become the main competitors for terrestrial dominance. A few seconds before the end of the Triassic period, the very first dinosaurs appear. Coelophysis, despite its relatively small size, represents the origin of the mighty Tyrannosaurus rex. It feeds on insects, lizards, and other small prey, and may also display scavenging tendencies. You might also encounter Proterozoic during this time. Don't worry though, it's completely vegetarian. A few amphibians survive the crisis as well. The temnospondyls, for example, enjoy relative peace in swampy environments. These represent some of the last labyrinthodont amphibians. Some amphibians that survived give rise to the lineages we know today, notably frogs and salamanders. In the oceans, nothosaurs roam the seas searching for food. They possess voracious appetites and share the waters with other emerging groups that remain quite discreet for the moment. No doubt they're biding their time, waiting to reveal their true capabilities. Here, we observe one of the first turtles and probably the very first mammal on our planet. These early mammals remain small and inconspicuous, but they represent the beginning of what will eventually become the dominant vertebrate group millions of years later. On December 15th, a new crisis strikes our blue planet. We don't fully understand what caused this extinction event. Could it have been the massive eruptions occurring during Pangaea's breakup? These volcanic events would undoubtedly have produced enormous quantities of carbon dioxide, significantly impacting global climate. Perhaps asteroids also struck Earth during this time. The Manicouagan crater in Canada and the Rochechouart crater in France bear witness to such devastating impacts. What we know for certain is that 70 to 80% of all species disappear during this transition. But from crisis comes opportunity. During the Jurassic period, dinosaurs experience an absolutely exceptional evolutionary radiation. They take full advantage of the crisis aftermath to completely conquer the territories they had long coveted. They adapt magnificently to their environments, filling vacant ecological niches and becoming increasingly diversified. This represents a veritable demographic explosion. Two major evolutionary lineages emerged during this time. The Ornithischian dinosaurs, mainly herbivores that moved in herds, already possess several representatives during the Jurassic. Depending on the specific environment or habitat, you might encounter Tuogiongosaurus, Stegosaurus, or various ankylosaurs roaming these ancient landscapes. Although these species are well known today, they're far from the only inhabitants of this prehistoric world. During those same hours, spanning December 15th through 18th, numerous ornithopods share the same territories. These include early relatives of iguanodon and various hadrosaurs, including creatures like Camptosaurus. The second major lineage, as you might expect, comprises the Saurischian dinosaurs. They include two distinct groups, the theropods, mostly bipedal carnivores, and the sauropods, generally massive quadrupedal herbivores. Several specimens represent this lineage, most notably Allosaurus. There's also Megalosaurus, reaching 7 meters in length, and the famous Archaeopteryx. This last creature is much smaller than the others, but equally exceptional and important in our planet's history. This remarkable animal undoubtedly represents the evolutionary link between dinosaurs and birds. The Jurassic also becomes the age of true giants, the impressive Diplodocus, which must have weighed around 15 tons and probably measured no less than 25 meters in length, can be observed strolling leisurely across the landscape. But there's also Brachiosaurus, which has nothing to envy about Diplodocus. A single vertebra from Brachiosaurus measures 70 centimeters in length. This colossal creature reaches 12 meters in height and approximately twice that in total length. While the Jurassic period was dominated by dinosaurs, the Cretaceous continues this reign with even greater intensity. Before returning to examine the masters of the land, let's discuss their changing environment. The landscape transformed somewhat during the Cretaceous, and for excellent reasons. The first angiosperms, flowering plants, begin appearing across the world. Insects had already evolved and diversified considerably with the appearance of flies during the Jurassic. But in the Cretaceous, evolutionary changes accelerate dramatically. Pollen and nectar from flowers aren't yet exploited by many creatures. This represents an incredible opportunity. Bees and butterflies experience a golden age of diversification. Melitosphex, the possible ancestor of modern bees, becomes one of the first insects to take serious interest in Archifractus and Montsechia, two aquatic flowering plants. It's now December 22nd, and the young mountain ranges are beginning to reshape the continental landscape. For several minutes now, certain evolutionary groups have been developing rapidly. New species emerge constantly, and some become very popular subjects of study, like Triceratops. This magnificent creature measures 7 meters in length and weighs approximately 8 tons of pure muscle and defensive capability. Apparently, it wasn't particularly good-natured. Battles must have been incredibly violent, especially when competing for mates. But Triceratops is far from the most impressive dinosaur in terms of sheer mass. The trophy for heavyweight champion undoubtedly belongs to Argentinosaurus. This titanic sauropod represents one of the largest land animals ever to walk our planet. New dinosaur adaptations emerge during the early hours of December 24th. Feathers, although probably present during the Jurassic, become much more common features during the Cretaceous. We observe them in creatures like Microraptor and Sinosauropteryx. It's December 25th, Christmas Day, and life is about to receive a very strange gift indeed. The age of reptiles approaches its tragic conclusion. Major volcanic eruptions coincide with the impact of a massive asteroid that crashes into what is now Mexico's Yucatan Peninsula. The crater measures 180 kilometers in diameter. Imagine the absolutely devastating power of this cosmic impact. Earth becomes plunged into darkness, choked by dust, gas, and acid rain. Life quickly suffocates under these hellish conditions. Ongoing volcanic eruptions exacerbate the already dire situation. For several seconds on our cosmic calendar, animals fall one by one. On December 26th, they all disappear. Only the mammals, which had maintained a low profile until this moment, will take advantage of the vacant ecological spaces left by the dinosaurs to develop and diversify dramatically. Now we reach the final era of our planet's history. It's somewhat mind-boggling to realize that this represents the period we know best, the era when Homo sapiens eventually appeared. Yet, there are only a few days remaining before the end of our cosmic year. We humans are truly insignificant compared to the vast length of Earth's incredible history. Mammals gradually establish themselves on all continents and diversify extensively. Some groups, like marsupials, become restricted to specific geographic zones, mainly due to plate movements that confine them to isolated land masses like Australia. In the early morning hours, around 6 a.m. on our final day, the first primate appears. Darwinius massillae, christened Ida by scientists, represents a lemur-like creature. According to researchers who studied its fossilized skeleton, this remarkable animal serves as our oldest common ancestor. It leads not only to modern lemurs, but also to apes in a broader sense, and ultimately to humans. You can observe its opposable thumb very clearly in fossil specimens. It feeds on seeds, leaves, and various fruits, representing a crucial evolutionary stepping stone toward more complex primates. A few hours later, around 10 o'clock a.m., India separates from the African continent and collides with the Eurasian plate. This collision follows the complete closure of the Tethys Ocean, which disappears entirely into the subduction zone bordering the Eurasian continent. The Indian continental crust, being lighter than oceanic crust, doesn't subduct. Instead, it indents dramatically into the Eurasian continental mass. Our planet's greatest mountain range, the Himalayas, is born from this colossal collision. Simultaneously, numerous new animal species continue appearing. All the biological groups we recognize today gradually emerge during this time. The continents increasingly take on the familiar shapes we know from modern geography. Seasonal patterns begin marking the rhythm of Earth's changing landscapes in ways that become increasingly recognizable to modern observers. Around 8 a.m. on December 31st, the first hominids finally make their appearance in our cosmic timeline. Only a few hours later, at approximately 11:50 p.m., a large-scale volcanic eruption at Mount Toba in Indonesia sends massive amounts of ash and dust into the atmosphere. This event lasts less than 1 second on our cosmic scale, equivalent to a few decades in real time. This volcanic winter causes the loss of almost 60,000 individuals from early human populations, creating a severe genetic bottleneck that affects our species' development. It's now 11:56 p.m., and Cro-Magnon humans, our closest prehistoric relatives, finally established their presence on Earth. But there are only 4 minutes remaining to accommodate them in our cosmic calendar. At 11:57 p.m., ice ages and interglacial periods follow one another in rapid succession. Despite harsh climatic conditions, many species manage to survive these challenging times. This doesn't include the woolly mammoth, which becomes extinct at precisely 11:58 p.m. But human populations continue proliferating and spreading across the globe. We're now discussing truly modern humans, Homo sapiens, in the fullest sense. It's 11:59 p.m., just seconds remaining on our cosmic clock. We find ourselves in the Sahara Desert. You might not remember this, but this land was once lush, green, and humid. Many animals, including early humans, took full advantage of the abundant natural resources this region offered. But climatic conditions gradually become dry and arid. Survival becomes too difficult in such an environment. Human populations migrate toward the Nile Valley, laying the foundations for what will eventually become Egyptian civilization. Now, we've existed since 4:09 p.m. on this cosmic day, but Cro-Magnon humans have been present for only 4 minutes. One of humanity's oldest ancient civilizations emerged merely 27 seconds ago on our timeline. We're now just seconds away from the present moment. It becomes impossible to examine our recent history in greater detail, whether discussing human development, the evolution of fauna and flora, or Earth's geological processes in general. Whether we consider our planet's story in terms of vast numbers or on this compressed scale, the dimension of time remains absolutely dizzying. Earth's history represents what makes our world such an exceptional planet in the cosmos. Looking ahead, Earth's future timeline stretches far beyond human imagination. Our planet will continue evolving, continents will keep moving, and life will persist, adapting to ever-changing conditions. The story we've traced from cosmic dust to complex civilizations represents just the beginning of Earth's magnificent journey through time. The secrets buried beneath our feet tell tales of unimaginable transformation, catastrophic events, and remarkable resilience. Every rock formation, every fossil, every geological layer serves as a chapter in this incredible narrative that spans billions of years. From the hellish Hadean landscape to the explosion of Cambrian life, from devastating mass extinctions to triumphant evolutionary radiations, our planet's history reveals the dynamic, ever-changing nature of the world we call home. This magnificent journey into prehistory continues unfolding around us every single day, reminding us that we're part of something infinitely larger and more wondrous than ourselves. The complete history of Earth represents not just a story of the past, but a foundation for understanding our present and imagining our future on this remarkable blue planet spinning through the cosmos. As we stand at the threshold of modern times in our cosmic calendar, we're about to witness Earth's next chapter unfold. But hold on tight, because what comes next will challenge everything you thought you knew about our planet's future. Picture this mind-bending scenario. In just 1,000,000 years from now, which is essentially a blink of an eye in geological terms, Earth won't appear dramatically different from space. Sure, the continents will have shifted, but only by about 45 to 60 kilometers from their current positions. The sun will continue its daily dance across our skies, rising every 24 hours, and our faithful moon will still orbit our world approximately once every month. But beneath this apparent stability, profound transformations are already set in motion. In many regions across our planet, irreversible geological processes are actively reshaping the landscape as we speak. The vulnerable coastlines that define our modern world will change in particularly dramatic ways. Consider this fascinating example. Off the southeast coast of Hawaii, an active submarine volcano has already risen over 3,000 meters from the ocean floor. This underwater mountain continues growing every single year. In 1,000,000 years, a brand new island will emerge from the Pacific waves, already christened Loihi by scientists who study these incredible processes. Meanwhile, the extinct volcanic islands to the northwest, including the familiar names of Maui, Oahu, and Kauai, will gradually shrink under the relentless influence of wind and ocean waves. It's a perfect example of Earth's constant cycle of creation and destruction, building new land while simultaneously eroding the old. When we examine the forces that will shape Earth's future geography, researchers conclude that the most active factor will be the advance and retreat of our oceans. Changes in volcanic activity beneath the seafloor will take enormous amounts of time to affect global geography, but their impacts prove profound. Depending on the amount of lava that solidifies on the ocean floor, sea levels can fluctuate significantly during periods when volcanic activity slows down. When rocks at the bottom cool and settle, dramatic drops in sea level can occur. Scientists believe this process caused the sharp decline in ocean levels just before major extinction events in our planet's past. The presence or absence of large inland seas, such as our Mediterranean, combined with the reunion and breakup of continents, leads to major transformations in coastal areas worldwide. To imagine what our world might look like hundreds of millions of years in the future, we must examine clues from the past to understand what lies ahead. Global tectonic processes will continue playing crucial roles in reshaping our planet's face. Today, vast oceans separate the Americas from Eurasia, Africa, Australia, and Antarctica. But these immense land masses remain in constant motion, traveling at speeds of approximately 2 to 5 centimeters per year. That translates to roughly 1,500 kilometers of movement every 60 million years. Scientists can establish fairly precise vectors for this continental drift by studying the age of volcanic rocks on the ocean floor. Material near mid-ocean ridges appears quite young, no more than a few million years old. In contrast, volcanic rock near continental margins and subduction zones can exceed 200 million years in age. By analyzing all this geological data about ocean floor composition, researchers can essentially rewind the tape of global tectonics over time. This gives us remarkable insights into how terrestrial continents have moved over the last 200 million years. Based on this information, it becomes possible to project continental plate movements 100 million years into the future. Given current trajectories of movement across our planet, it appears that all continents are heading toward another collision. In approximately 250 million years, most of Earth's land mass will once again merge into a giant supercontinent. However, the exact structure of this future supercontinent remains hotly debated among scientists. Taking into account current continental movements, we can predict their trajectories for the next 10 to 20 million years with reasonable confidence. The Atlantic Ocean will expand by several hundred kilometers, while the Pacific Ocean shrinks by roughly the same distance. Australia will drift northward toward South Asia, and Antarctica will move slightly away from the South Pole, also heading toward Southern Asia. Africa will continue its slow northward journey across the Mediterranean Sea. In several tens of millions of years, Africa will collide with southern Europe, completely closing the Mediterranean and creating a mountain range comparable to the Himalayas at the collision site. So the world map, 20 million years from now, will still look somewhat familiar to us. But when modeling a map 100 million years in the future, most researchers identify some common geographical features that seem almost inevitable. For example, scientists agree that the Atlantic Ocean will exceed the size of the Pacific Ocean, becoming the largest water basin on Earth. According to one major theory called extroversion, the Atlantic Ocean will continue expanding, while the Americas eventually collide with Asia, Australia, and Antarctica. In the final stages of this supercontinent assembly, North America will close the Pacific Ocean to the east and collide with Japan. South America will wind clockwise from the southeast, joining the equatorial portion of Antarctica. All these pieces will combine in an astonishing continental puzzle, creating a single massive continent stretching from east to west along the equator. The extraversion model assumes that large convection cells in Earth's mantle beneath the tectonic plates will remain unchanged in their current form. In contrast, an alternative approach called introversion takes the opposite stance, referencing past cycles of closure and opening of the Atlantic Ocean. Today, both supercontinent theories remain popular among geologists. Whatever the outcome of this scientific discussion, everyone agrees that while Earth's geography will change significantly in 250 million years, it will still reflect patterns we can observe from the past. According to computer simulations, around 200 million years from now, average temperatures on Earth should fall slightly below 12 degrees Celsius. At the same time, global sea levels will drop by approximately 200 meters. In this configuration, conditions for complex life development will remain quite favorable at low and mid-latitudes. Only after around 400 million years will average surface temperatures fall to about 10 degrees Celsius, with ocean levels dropping more than 500 meters from their current position. In this scenario, all continents from north to south, even at moderate latitudes, will be covered by glaciers. Mountainous regions at equatorial latitudes will also become frozen. However, this cold period won't last forever. After another 200 to 300 million years, an equilibrium should establish itself between decreasing temperatures due to atmospheric changes and the increasing brightness of our sun. The temporary assembly of continents around the equator will help moderate the impact of ice ages and stabilize sea level changes. Where continents collide, mountain ranges will rise dramatically. Climate and vegetation patterns will transform, and oxygen and carbon dioxide levels in the atmosphere will fluctuate significantly. These changes will repeat throughout Earth's remaining history, following patterns we've already observed in the geological record. But our planet faces threats from beyond as well. Within 500 to 600 million years, a gamma ray burst or massive supernova explosion will likely occur less than 6,500 light years from Earth. Gamma ray bursts represent the most intense and energetic explosions in the universe, and astronomers believe they're linked to extremely powerful stellar explosions. Fortunately, we haven't yet observed a gamma ray burst close enough to fully understand their devastating potential. So far, these cosmic events have only been detected in other galaxies, far from our local neighborhood. But if such an event were to occur relatively close to us on a cosmic scale, as statistical models suggest will happen within 600 million years, it could trigger a mass extinction event. A gamma ray burst directed toward Earth and lasting just 10 seconds could destroy at least half of our planet's protective ozone layer. Large-scale ozone depletion would have catastrophic consequences for food chains, leading to the death of countless species. A gamma ray burst would annihilate life forms on Earth's surface and in the upper layers of our oceans, which currently supply significant amounts of oxygen to our atmosphere. Gamma rays also decompose oxygen and nitrogen present in the atmosphere, transforming these gases into nitrogen dioxide, better known as smog. This toxic cloud would envelop our planet, blocking sunlight and triggering a global ice age that could last for millions of years. Meanwhile, due to gravitational forces, our moon continues moving away from Earth. It has already drifted more than 20,000 kilometers farther from our planet since its formation. Within 600 million years, the lunar disk will no longer be able to completely cover the sun during eclipses. All future eclipses will be annular, with a ring of sunlight visible around the moon's silhouette. The fate of Earth becomes intimately linked to that of our sun, which, like all stars, cannot shine forever. 50 million years after the sun's formation, our star became what astronomers call a main sequence star. Since then, its brightness has increased in an almost linear fashion, rising by approximately 1% every 110 million years. Within 600 million years, our sun will undergo a gradual transformation, resulting in progressive increases in both brightness and heat output. This increase in solar luminosity will significantly impact our planet, delivering more radiation to Earth's surface than ever before. This enhanced solar energy will affect silicate minerals present on our planet, leading to increased weathering of these materials. This process will impact the carbonate-silicate cycle, a crucial geochemical process involving interactions between carbonate and silicate compounds. Increased weathering of surface rocks traps carbon dioxide in soil as carbonate compounds. As water evaporates from Earth's surface, rocks harden, leading to a slowdown in plate tectonics that eventually comes to a complete halt when oceans evaporate entirely. With reduced volcanism to recycle carbon into Earth's atmosphere, carbon dioxide levels begin falling dramatically. For hundreds of millions of years, Earth experiences intense cold with average surface temperatures around 10 degrees Celsius. But the sun's increasing brightness eventually triggers rising temperatures, generating a cascade of problems. The first signs of trouble appear within 600 million years, but the situation becomes critical only when average temperatures reach 47 degrees Celsius. At this point, solar luminosity will be 10% higher than today. From that moment forward, Earth begins losing water progressively, fundamentally modifying its atmosphere. Our planet transforms into what scientists call a humid greenhouse due to massive evaporation of surface water. The amount of water in the stratosphere increases dramatically. These water molecules break down under the sun's ultraviolet radiation through photodissociation. Hydrogen escapes from the atmosphere while oxygen accumulates. The main consequence should be the complete disappearance of Earth's oceans within approximately 1.1 billion years. This water vapor in the stratosphere undergoes chemical decomposition, separating into oxygen and hydrogen. Major atmospheric changes follow inevitably. Higher temperatures cause oceans to absorb more carbon dioxide, a gas absolutely essential for plant life. This absorption reduces atmospheric carbon dioxide, creating dangerous imbalances in plant life cycles. Current scientific forecasts indicate that our planet will support highly organized life for another 600 million years. After this period, the sun's increasing brightness will have devastating impacts on the biosphere. The emerging scenario appears deeply troubling, as Earth will progressively lose precious water while simultaneously experiencing shortages of gases vital for plant development. Together, these elements threaten the delicate balance of our entire ecosystem. High temperatures projected for the future will cause oceans to absorb even more carbon dioxide, disrupting biological processes essential for plant survival and accelerating problems associated with water loss and atmospheric degradation. We approach what scientists call Earth's carbon dioxide compensation limit, a critical threshold where the balance between carbon dioxide and oxygen becomes unsustainable for photosynthesis. In approximately 600 million years, atmospheric carbon dioxide levels will fall below those needed to maintain C3 carbon fixation, the photosynthetic process used by most trees and plants. Some plants using C4 carbon fixation can survive with carbon dioxide concentrations as low as 10 parts per million. Currently, 99% of plants rely on C3 photosynthesis. Their ability to convert sunlight into energy gradually declines, leading to general reductions in plant biomass across the globe. When atmospheric carbon dioxide levels fall below critical values, the survival of complex plants becomes impossible. They require minimum concentrations of around 10 parts per million to function. Evolution may enable some organisms to adapt by developing more efficient photosynthetic mechanisms, but these adaptations have limits. When levels fall below this threshold, complex plants begin dying en masse, leading to dramatic reductions in oxygen production. This decrease, combined with continued consumption by living organisms and oxidation of organic carbon in sedimentary rocks, creates a gradual decline in atmospheric oxygen until it reaches zero within a few million years. Researchers estimate that plants using C3 photosynthesis should disappear within 600 million years, while C4 plants may survive until 840 million years at the latest. This massive disappearance of plant life will have absolutely devastating consequences for all living beings as we know them today. Plants form the foundation of virtually every food chain, providing sustenance and energy for herbivorous animals. Their decline means drastically reduced food resources for plant-eating creatures, which suffer severe population declines as ecosystem balance collapses entirely. Without plants producing oxygen through photosynthesis, animals face catastrophic situations. Large warm-blooded animals such as mammals and birds will probably disappear first due to their higher oxygen requirements compared to smaller creatures. As atmospheric oxygen levels fall and temperatures rise relentlessly, placental mammals become particularly vulnerable. Not only do they require more oxygen than non-placental mammals, but embryonic development proves highly sensitive to excessive heat exposure. Large herbivorous mammals will struggle with diminishing food resources as plant availability declines across all habitats. Small mammals will be slightly less affected due to lower oxygen requirements and better surface-to-volume ratios that facilitate heat dissipation. Placental mammals experience higher body temperatures than marsupials and monotremes, making them potentially more sensitive to rising global temperatures. Birds may adapt better to survival than larger mammals due to their generally smaller size and correspondingly lower oxygen needs. Migratory birds in particular would be better equipped than similar-sized animals thanks to their ability to travel vast distances searching for cooler refuges. Nevertheless, the number of such refuges will decrease as temperatures continue rising worldwide. These remaining habitable areas will likely exist at higher altitudes where less land surface is available, severely limiting population sizes. As species migrate to higher elevations seeking relief from heat, competition for limited resources intensifies dramatically. Cold-blooded vertebrates, such as fish, amphibians, and reptiles, could survive longer than warm-blooded animals in this scenario. They possess better heat tolerance and generally require less oxygen for survival. However, reduced water availability makes some amphibian species more vulnerable in such harsh environments. Fish species will also face significant risks, although rapid evaporation from oceans won't occur immediately at this stage. Marine species may have better survival prospects than freshwater species due to the greater volume of ocean water compared to inland water bodies. For cold-blooded animals, ambient temperature directly influences metabolic rate. Increases in environmental temperature lead to higher metabolic rates and therefore greater food requirements. As a result, surviving species could face starvation as food sources become increasingly scarce. Reptile species whose sex determination depends on temperature will prove more sensitive to rising global temperatures. This biological mechanism could lead to reproductive failures and population crashes among many reptilian groups. Invertebrates could represent the last animals surviving on Earth before all animal species finally disappear. Some insects, such as beetles, can survive temperatures reaching 56 degrees Celsius. In general, terrestrial life will initially prove more vulnerable than marine life due to water's temperature regulating effects. However, the loss of terrestrial vegetation leads to reduced nutrients reaching ocean ecosystems. Isolated communities in marine environments, such as animal populations living near volcanic vents, will probably survive longer than most other life forms. Depending on oxygen's half-life in the atmosphere, animal life could persist for up to 100 million years after plant disappearance. Some cyanobacteria and phytoplankton could survive without traditional plants, as they tolerate carbon dioxide levels as low as 1 part per million. These hardy microorganisms could persist until the atmosphere becomes too depleted of carbon dioxide to allow any form of photosynthesis whatsoever. Research suggests that specific forms of animal life might persist even after most plant life on Earth has vanished entirely. Scientists have used fossil evidence from formations like the Burgess Shale in British Columbia, Canada, to study ancient climate conditions. They've applied this knowledge to predict future scenarios when global temperatures rise due to our warming sun and decreasing oxygen levels. Initially, researchers expected some insects, lizards, birds, and small mammals to persist alongside marine life. However, without continuous oxygen supply from plant photosynthesis, they estimated that animals would probably die from asphyxiation eventually, even if sufficient oxygen remained in the atmosphere thanks to persistent photosynthetic organisms. Steadily rising global temperatures would lead to progressive biodiversity loss. As temperatures continue climbing, the last surviving animals will be forced to migrate toward polar regions or seek refuge underground. These final survivors would mainly remain active during polar night periods, entering dormancy during polar day periods due to intense heat exposure. Much of Earth's surface would become an arid desert, with life concentrating primarily in ocean environments. Due to decreased input of organic matter from land and reduced dissolved oxygen levels, marine life would also disappear following similar patterns to terrestrial ecosystems. This process would begin with freshwater species extinction and conclude with the loss of invertebrates, particularly those not dependent on living plants. Creatures like termites or organisms found near hydrothermal springs, such as specialized worms, might represent the final holdouts of complex life on our planet. Without adequate carbon dioxide, photosynthesis eventually becomes impossible everywhere. Without plant life to recycle oxygen back into the atmosphere, free oxygen and the protective ozone layer will disappear entirely. This allows intense levels of deadly ultraviolet radiation to reach Earth's surface, sterilizing any remaining life forms. As a result of these interconnected processes, multicellular life forms could become extinct within approximately 800 million years. Eukaryotic organisms might disappear within 1.3 billion years, leaving only simple prokaryotic bacteria to face an increasingly hostile world. Our magnificent journey through Earth's complete history reveals a planet of extraordinary resilience and constant transformation. From cosmic dust to complex civilizations, from devastating extinctions to triumphant evolutionary radiations, Earth's story continues unfolding around us every single day. The secrets buried beneath our feet tell tales that dwarf any human drama, reminding us that we're part of something infinitely larger and more wondrous than ourselves. This prehistoric journey into Earth's past provides the foundation for understanding our present and contemplating our future on this remarkable blue planet spinning through the vast cosmos. The sun's nuclear fusion reactions will continue generating energy, but fundamental changes approach that will reshape our entire solar system. To understand the sun's energy production, we need to examine what happens at its core. Every second, nuclear fusion converts approximately 500 tons of hydrogen into helium. This cosmic alchemy progressively reduces the number of particles while maintaining the tremendous energy output that powers all life on Earth. This ongoing process explains why our star's luminosity increases gradually over time. Thanks to an effective greenhouse effect, Earth has maintained relatively stable temperatures throughout most of its history, apart from periodic ice ages that have shaped evolutionary development. For hundreds of millions of years, our planet hasn't experienced significant changes in ocean mass due to the near equilibrium between mantle water inflows and outflows. Maintaining liquid water on Earth requires establishing a delicate balance between absorbed solar energy and energy radiated back into space. This equilibrium proves crucial for life's survival as we understand it. When greenhouse gas concentrations in Earth's atmosphere increase, as currently occurs due to human activities, a new energy balance emerges. The enhanced greenhouse effect creates an additional thermal blanket, causing surface temperatures to rise. Earth possesses an integrated regulatory mechanism called the carbonate-silicate cycle, which controls atmospheric carbon dioxide levels to maintain stable climate conditions. Unfortunately, this natural thermostat operates on timescales spanning millions of years, making it ineffective for addressing rapid climate changes. Progressively, even during the current period of hydrogen combustion, our sun inexorably increases in temperature and brightness. Approximately 4.5 billion years ago, at its formation, solar luminosity equaled only 70% of today's output. By the time of the Great Oxygenation Event 2.4 billion years ago, brightness had already reached 85% of current levels. For the next billion years, our sun will continue producing nuclear energy by converting hydrogen into helium through fusion reactions. This represents what nearly all stars accomplish during most of their active lifespans. As hydrogen transforms into helium within the solar core, average molecular weight increases, leading to rising core temperatures and accelerated fusion reactions. This gradual process leads to steady increases in stellar energy output. Consequently, our sun will shine progressively brighter as eons pass. When incoming energy increases, it contributes to global warming effects, precisely what occurs as solar luminosity gradually intensifies. Although Earth's climate experiences shorter-term variations due to seasonal changes, atmospheric composition modifications, including human-generated greenhouse gases, volcanic dust, and astronomical cycles, our planet's surface undergoes slow but steady warming due to increasing solar luminosity. Over extended periods, perhaps spanning several 100 million years, Earth's feedback mechanisms may partially offset these effects. Greater thermal energy intensifies evaporation, hence increasing cloud cover that reflects more sunlight back into space. Enhanced thermal energy also accelerates rock weathering, promoting greater carbon dioxide absorption and reducing greenhouse gas concentrations. These negative feedback loops will preserve life-supporting conditions on Earth for considerable time. However, at some point, our planet's atmosphere will reach a critical threshold where it can no longer maintain stable energy balance, leading to amplification of greenhouse effects. This phenomenon resembles what scientists call runaway greenhouse conditions characterized by positive feedback loops. As planetary surfaces warm, atmospheric water evaporation increases. Water vapor acts as a powerful greenhouse gas, reinforcing warming effects and further heating surface temperatures. For several million years, cellular life can persist under such extreme conditions. Nevertheless, the critical moment will inevitably arrive when greenhouse effects become completely uncontrollable, warming Earth's surface until oceans reach states of complete evaporation. Despite increased water vapor concentrations near Earth's surface, no liquid oceans will remain. Subsequently, it will take only a few 100 million years for complete ocean evaporation, transforming our atmosphere into an endless reservoir of superheated steam. When ultraviolet radiation interacts with atmospheric gases, it causes further heating effects. More thermal energy transfers to atmospheric water when it encounters extreme ultraviolet wavelengths. Consequently, water absorbs additional energy and heats faster, leading to increased evaporation rates and more rapid water loss from Earth's surface. Another way to understand this process involves the concept of habitable zones, which refer to orbital regions around stars where planets can maintain liquid water given suitable atmospheric conditions. Currently, the inner edge of our Sun's habitable zone sits at approximately 95% of the Earth-Sun distance. Our planet will eventually become completely devoid of life as these processes unfold. The real catastrophe arrives later as solar luminosity continues increasing. The inner boundary of the habitable zone will migrate progressively outward from the Sun. Determining exactly when the habitable zone's inner edge reaches Earth's orbit proves challenging, but estimates suggest this occurs around 1 billion years from now. Some extremophile organisms may survive in refuges at higher latitudes or deep underground, but these represent only temporary remnants of once flourishing biospheres. This situation could mirror the symmetry of life's original emergence on Earth. Most likely, our planet will follow Venus's fate, becoming a scorching, barren world as our Sun's habitable zone shifts toward the outer solar system. Mars currently lies within this expanding habitable zone. It's possible that Martian surface temperatures will gradually increase as carbon dioxide and water currently frozen beneath the soil release into the atmosphere, creating greenhouse effects. This warming could heat Mars until it reaches conditions comparable to contemporary Earth, potentially offering new opportunities for life. According to computer models, our moon's presence helps stabilize Earth's axial tilt, preventing dramatic climate fluctuations. This stability results from the moon accelerating our planet's rotational axis precession, avoiding resonances between rotational and orbital precession cycles. Tidal acceleration caused by lunar gravity slows Earth's rotation, while increasing the distance between our planet and its satellite. As the moon's orbital radius continues expanding, the stabilizing influence will diminish over time. Eventually, gravitational disturbances will probably lead to chaotic variations in Earth's axial tilt. The rotational axis could tilt to angles as extreme as 90 degrees relative to the orbital plane. Scientists estimate this will occur between 1.5 and 4.5 billion years from now. High obliquity angles would probably trigger dramatic climate changes that could compromise planetary habitability. When Earth's axial tilt exceeds 54 degrees, annual solar radiation at the equator becomes lower than at the poles. Planets can potentially maintain obliquity angles between 60 and 90 degrees for periods lasting 10 million years. The likely consequence involves cessation of ocean evaporation, plate tectonics, and the entire carbon cycle. This could happen approximately 2 to 3 billion years from now, when our planet's magnetic dynamo might cease functioning, leading to magnetosphere decomposition. This would accelerate the loss of volatile atmospheric elements into space. In 2.8 billion years, Earth's surface temperature will average 147 degrees Celsius even at the poles. Life becomes reduced to single-cell colonies surviving in isolated microenvironments such as underground caverns, disappearing everywhere else. Every second, our sun emits solar wind toward Earth, corresponding to flows of millions of tons of protons and electrons. These particles encounter Earth's magnetic field, which extends over 70,000 kilometers and originates from our planet's iron-nickel core. The core consists of a solid inner section and a liquid outer layer approximately 2,000 kilometers thick. Continuous circulation of this liquid metallic layer generates Earth's protective magnetic field. Currently, the inner core's radius increases at roughly 0.5 millimeters per year at the outer core's expense. Virtually all energy required to power this magnetic dynamo comes from the inner core. Within 3 billion years, the inner core will absorb most or all of the outer core, resulting in an almost entirely solidified core composed mainly of iron and heavy elements. The remaining liquid envelope will consist primarily of lighter elements that undergo less mixing. Tectonic plate dynamics depend on heat transfer from Earth's core to the surface through mantle convection, sometimes combined with thermal conduction. When heat plumes reach the crust, they release thermal energy and become displaced by new hot plumes. This horizontal movement in the upper mantle provides the driving force behind tectonic plate motion. However, as Earth cools over time, the liquid outer core gradually solidifies. This solidification reduces mantle convection, limiting available power for plate movement. Eventually, after approximately 3 billion years, convection will cease entirely, ending tectonic plate movements. If plate tectonics stop, Earth's interior will cool less efficiently, slowing or halting inner core growth. In either scenario, this could lead to magnetic dynamo failure. Without a functional dynamo, Earth's magnetic field will weaken rapidly over geologically brief periods of around 10,000 years. Magnetosphere disappearance will increase erosion of light atmospheric elements, particularly hydrogen, into space. This creates conditions less conducive to life as we know it. In approximately 4 billion years, rising surface temperatures will trigger uncontrollable greenhouse effects, creating conditions more extreme than those on contemporary Venus. This will heat the atmosphere and raise surface temperatures above 500 degrees Celsius, sufficient to melt planetary surfaces in some regions. Nevertheless, much of the atmosphere will persist until our sun enters its red giant phase. At that point, Earth's biological signatures will vanish, replaced by indicators caused by non-biological processes. From then onward, all traces of our planet's life history will be completely erased. In 4.5 billion years, interactions between the Andromeda Galaxy and our Milky Way will create a new galaxy. Scientists have named Milkomeda the Andromeda Galaxy, also designated M31, represents a spiral galaxy containing up to 1,000 billion stars. Compared to our Milky Way's 300 to 400 billion. Composed of gas and dust, it maintains a flattened disk shape with a central bulge. Originally located 2.55 million light-years away, Andromeda has gradually approached the Milky Way at speeds of 120 kilometers per second. Initially, the two galaxies won't directly collide. Being separated by vast distances, stars will pass each other without head-on impacts before moving apart. Later, this cosmic choreography leads to renewed approach, followed by strong gravitational interactions between both galaxies. Their orbits become strongly affected by chaotic gravitational forces during galactic interpenetration. The result, after 2 billion years, involves birth of a gigantic system with minimal interstellar gas. This new elliptical galaxy, Milkomeda, will contain stars scattered throughout a spherical distribution rather than the spiral arms of its parent galaxies. This collision won't disrupt planetary orbits within our solar system. While gravity from passing stars could detach planets into interstellar space, distances between stars remain so vast that the probability of Milky Way-Andromeda collision causing disruption to any given star system proves negligible. Although our solar system as a whole could be affected by these galactic events, the sun and planets will unlikely be disturbed directly. The new galaxy will experience renewed star formation as remaining gas becomes rapidly consumed, but star birth will cease and Milkomeda will slowly fade as new stars eventually die. In 5 billion years, our sun will leave its main sequence phase and begin transforming into a red giant. Having exhausted hydrogen reserves in its core, energy released during hydrogen fusion fuels the dynamic activity of particles that exert powerful outward pressure. This pressure enables solar expansion without gravitational collapse. Until now, this balance has been maintained successfully. But at 5 billion years, this equilibrium will no longer exist. Although our sun still contains abundant hydrogen nuclei, virtually none remain in its core. Hydrogen fusion produces helium with heavier, denser nuclei than hydrogen. Core temperatures reach approximately 15 million degrees Celsius, while hydrogen fusion requires 10 million degrees. Helium fusion demands temperatures around 100 million degrees Celsius. Our sun remains far below this threshold, so as helium replaces hydrogen in the core, fusion fuel supplies will diminish. Pressure from energy production will decline, allowing gravity to dominate and cause solar implosion. As this gigantic mass collapses inward, solar temperatures will rise dramatically. Despite extreme pressure and temperature, helium fusion remains impossible. Hydrogen then triggers secondary fusion within thin layers surrounding the helium core. As hydrogen fusion proceeds at tremendous rates, outward thrust becomes much more intense than before. Our sun swells to colossal proportions, reaching diameters exceeding 100 million kilometers, nearly 100 times its current size, transforming into a pulsating red giant thousands of times brighter than today. It abandons its main sequence status to become a red giant. Naturally, planets within our solar system will be directly affected by this transformation. The sun, with diminished mass, exerts reduced gravitational attraction, enabling planets to migrate to more distant orbits. But do planets travel far enough to escape the sun's expanding diameter? Mercury loses this race, becoming swallowed and briefly vaporized. Mars, orbiting farther out, escapes unharmed. Venus proves fortunate as solar expansion halts just before reaching its new orbital position. Earth also survives initially. Nevertheless, conditions become fundamentally different. Both Earth and Mars will rotate synchronously with the Sun. Average temperatures reach several thousand degrees. What does sunrise look like from Earth under these circumstances? Instead of a warm, cheerful yellow disk, a gigantic red circle slowly emerges above the horizon. Mars won't escape this fate much longer. Atmospheric warming begins, and potential life forms on this planet won't survive another billion years. Two new orbits now occupy our solar system's habitable zone, Jupiter and Saturn. Although neither planet supports life directly, their respective moons could become suitable locations for primitive life emergence once temperatures rise sufficiently. Simple organisms could potentially develop on Saturn's moons, Enceladus or Titan, or Jupiter's moon, Europa. Most of Earth's atmosphere will gradually escape into space. Our planet's surface will transform into a lava ocean with floating continents of metals and metal oxides, alongside icebergs of refractory materials. Surface temperatures will rise dramatically, exceeding 2,000 degrees Celsius. Over 12 billion years old, the Sun's most rapid expansion phase as a red giant occurs during final stages approximately 7.4 billion years from now. At this point, solar expansion will likely reach maximum radius around 1.2 astronomical units. Our Sun will have lost more than one-third of its current mass, dispersed initially through intense solar winds. This mass loss causes planetary orbits to expand considerably. Considering only this phenomenon, Venus and Earth could probably escape incineration. However, other studies suggest both planets would still be absorbed due to tidal interactions with tenuous gases from the Sun's expanded outer envelope. Forecasts for our planet's ultimate fate appear rather gloomy. Earth's gravitational interaction with the Sun's outer atmosphere will cause orbital decay. Drag effects from the solar chromosphere will progressively reduce Earth's orbital distance. These effects will partially compensate for solar mass loss, making it likely that our Sun will eventually engulf Earth approximately 7.59 billion years from now. Solar atmospheric drag can also cause lunar orbital disintegration. As the Moon's orbit approaches 18,470 kilometers distance, it crosses Earth's Roche limit, meaning tidal forces exerted by our planet will tear the Moon apart, transforming it into a ring system. Most orbital ring material will decay, and residual debris will impact Earth. Consequently, even if the sun doesn't directly engulf our planet, Earth could lose its moon entirely. Our planet's decaying trajectory toward the sun may eliminate Earth's mantle, leaving only its core. Eventually, even Earth's core would be destroyed within 200 years. According to this scenario, the sun's red giant phase will simply destroy Earth, which will evaporate into hot solar atmosphere and cease existing. But our sun story as a red giant doesn't end there. As hydrogen nuclei continue fusing around the core, more helium flows into the center and temperatures rise even higher. The cycle accelerates as hydrogen fusion in shells around the core intensifies, and helium accumulation at the center increases. This phase lasts 500 million years before the core finally reaches temperatures required for helium fusion, a process producing carbon and oxygen. This transition from hydrogen to helium fusion features spectacular eruptions, during which the sun contracts to more consistent subgent structure. This new equilibrium proves short-lived. 100 million years later, carbon and oxygen nuclei displace helium from the core into neighboring layers, just as helium previously displaced hydrogen. Combustion of oxygen and carbon requires higher temperatures, at least 600 million degrees Celsius. This time, the core never reaches temperatures required to restart nuclear reactions. Solar mass isn't sufficient to achieve temperatures necessary for fusing carbon and oxygen nuclei into heavier, more complex elements. The helium shell continues burning while the core continues contracting until quantum mechanics halts implosion. This quantum mechanism acts as repulsion, as if electrons refuse further compression, bringing solar contraction to an end. Outer layers continue expanding and cooling before scattering across the cosmos. All that remains is a staggeringly dense ball of carbon and oxygen known as a white dwarf. It will continue glowing for several billion more years. Fusion reactions cease when temperatures become insufficient. Solar thermal energy dissipates gently into space, leaving a dark, cold sphere. In 9 billion years, our sun, with mass equal to 54% of its current value, becomes a white dwarf composed of carbon and oxygen. Our sun is now dead, its core exposed. Its gravitational attraction on orbiting bodies like planets, comets, and asteroids has weakened due to mass loss during previous stages. All remaining planetary orbits will expand significantly if Earth still exists. Its orbit will be twice as distant as the orbit we know today. All planets become dark, icy, and completely devoid of life. They continue orbiting their dead star at reduced speeds due to increased distance and diminished gravity. More than 4 billion years later, the white dwarf sun has cooled to 2,000 degrees Celsius. Its luminosity falls below 3 billionths of current levels. Heat becomes unmeasurable as radiation becomes so weak it drowns in cosmic microwave background radiation. Our sun gradually transforms from white dwarf to black dwarf. The prospects for planetary destruction aren't merely speculative, but based on solid scientific predictions derived from our current understanding. Although we possess knowledge of Earth's distant future, it remains our responsibility to shape the immediate future. This perspective raises fundamental questions about life's future on Earth and our responsibility as a species aware of this potential destiny. It's crucial that we deepen scientific knowledge, develop environmental preservation strategies, and explore innovative solutions to prepare our planet's biodiversity and sustainability. While these cosmic events may seem distant on human timescales, they remain inescapable realities in our solar system's natural evolution. Understanding these phenomena and their implications enables us to better appreciate the importance of preserving our environment and exploring new approaches to ensure sustainable futures for generations to come. This represents the ultimate aspiration of a scientifically literate society, and our only hope of postponing as long as possible the inevitable conclusion of human existence. Our magnificent journey through Earth's complete history, from cosmic dust to the distant future, reveals a planet of extraordinary resilience, constant transformation, and ultimate impermanence. The story continues unfolding around us every day, reminding us that we're part of something infinitely larger and more wondrous than ourselves, yet also infinitely precious and finite. The secrets buried beneath our feet continue to reveal themselves as we approach the most mind-bending chapters of Earth's story. We've witnessed our planet's birth from cosmic chaos, watched life emerge from primordial soup, and observed the rise and fall of countless species. But what we're about to explore next will challenge everything you thought you knew about the nature of time itself. Picture this staggering reality. We've just experienced the most dramatic extinction event in Earth's history, the Great Dying that wiped out 95% of all species. Yet here we stand at December 11th on our cosmic calendar, and life is about to stage the most incredible comeback you could possibly imagine. But there's something absolutely extraordinary about what happens next. From this point forward, the pace of change accelerates beyond anything we've witnessed so far. If you thought the previous chapters were intense, you haven't seen anything yet. The remaining weeks of our cosmic year will pack more drama, more evolutionary leaps, and more breathtaking transformations than entire months that came before. Why does everything suddenly speed up? The answer lies in the fundamental nature of evolution itself. Each major extinction creates vacant ecological niches, empty spaces in nature's grand design that life rushes to fill with explosive creativity. It's like clearing a massive forest and watching an entire ecosystem rebuild itself from scratch, but happening on a planetary scale. December 11th marks the beginning of what scientists call the Mesozoic era. And honestly, calling it the Age of Reptiles doesn't do justice to the absolute insanity that's about to unfold. We're entering a period where life doesn't just recover from near total annihilation. It reinvents itself in ways so spectacular they seem pulled from the wildest science fiction. In the aftermath of this greatest biological crisis, flora and fauna begin regaining vitality with shocking speed. Life returns, but it's unlike anything that came before. The Triassic period has the unique distinction of being the only era in Earth's history to begin and end with mass biological crises. It's bookended by catastrophe. Yet what happens in between defies all expectations. It takes just minutes for our planet to catch its breath. Plants, remarkably, survive the Great Dying rather well. The hardy survivors we encountered earlier, those resilient lycopods and sphenopsids, along with the distinctive Glossopterus, remain present across the landscape. This surviving flora provides the foundation that enables the spectacular return of animal life. Gradually, vegetation in the northern hemisphere takes on a completely new appearance. Conifers become increasingly numerous and diversified, spreading across vast territories like nature's own reforestation project. But it's among the animals where we witness the most dramatic transformations. Some groups find themselves stripped of their former dominance, while others seize the opportunity to fill vacant spaces. Until now, amphibians have occupied significant ecological territory, and synapsids have maintained fairly stable populations. But something revolutionary is happening. Diapsid reptiles are gradually conquering the continent with unprecedented success. The archosaurs, which had been timid and few in number during previous eras, suddenly explode into prominence. They take full advantage of this biological crisis to claim empty ecological niches with remarkable efficiency. A few minutes after midnight on December 12th, these archosaurs experience an evolutionary radiation so dramatic it reshapes the entire planet. They will eventually give rise to lineages that include crocodiles, dinosaurs, and Proterozoics. During this Triassic period, crocodilomorphs and dinosauromorphs become the primary competitors for terrestrial dominance. The stage is being set for the most famous chapter in Earth's biological history. Just seconds before the Triassic period ends, something extraordinary happens. The very first dinosaurs make their appearance on our cosmic stage. Coelophysis, despite its relatively modest size, represents the ancestral line that will eventually produce the mighty Tyrannosaurus rex. This early predator feeds on insects, lizards, and other small prey, possibly displaying scavenging behaviors as well. You might also encounter Plateosaurus during this time, but don't worry about this one. It's completely herbivorous, representing an early experiment in plant eating among dinosaur lineages. Meanwhile, a few amphibians managed to survive the ongoing transformations. The temnospondyls, for example, find refuge in swampy environments as some of the last representatives of the labyrinthodont amphibians. Some surviving amphibians give rise to lineages we recognize today, notably the ancestors of modern frogs and salamanders. In the oceans, nothosaurs cruise the seas with voracious appetites, sharing the waters with other emerging groups that remain relatively inconspicuous for now. They're probably waiting for the right moment to reveal their true potential. Here we observe some of the first turtles alongside what are probably the very first mammals on our planet. These early mammals remain small and unassuming, but they represent the humble beginnings of what will eventually become the dominant vertebrate group millions of years later. On December 15th, yet another crisis strikes our blue planet. We don't fully understand what triggers this extinction event. Could it have been massive eruptions occurring during Pangaea's dramatic breakup? These volcanic episodes would have produced enormous quantities of carbon dioxide, significantly impacting global climate systems. Perhaps asteroids also bombarded Earth during this transition. The Manicouagan crater in Canada and the Haut-Chouard crater in France serve as stark reminders of such devastating cosmic impacts. What we know with certainty is that 70 to 80% of all species disappear during this tumultuous period. But here's where the story takes an absolutely incredible turn. During the Jurassic period, dinosaurs experience an evolutionary radiation so spectacular it defies imagination. They seize the aftermath of crisis to completely dominate the territories they've long coveted. They adapt to their environments with stunning efficiency, filling vacant ecological niches and diversifying at an unprecedented rate. This represents nothing short of a demographic explosion. Two major evolutionary lineages emerge with distinct characteristics and survival strategies. The Ornithischian dinosaurs, primarily herbivores that move in coordinated herds, already possess several representatives during the Jurassic. Depending on specific environments and habitats, you might encounter magnificent specimens like Tuojiangosaurus, the iconic Stegosaurus, or various heavily armored ankylosaurs, but these famous species represent just the tip of the iceberg. During the hours spanning December 15th through 18th, numerous ornithopods share the same territories with early relatives of Iguanodon and various hadrosaur ancestors, including creatures like Camptosaurus that hint at the incredible diversity to come. The second major lineage comprises the Saurischian dinosaurs, divided into two distinct groups. The theropods, mostly bipedal carnivores with razor-sharp teeth and powerful claws, and the sauropods, generally massive quadrupedal herbivores that will grow to sizes almost beyond comprehension. Several iconic specimens represent this incredible diversity. Allosaurus stalks through these ancient landscapes as an apex predator. Megalosaurus, reaching 7 meters in length, demonstrates the formidable hunting capabilities of these early theropods. But perhaps most remarkable of all is Archaeopteryx, much smaller than its contemporaries, but equally extraordinary in its implications for the future. This remarkable creature represents the evolutionary bridge between dinosaurs and birds, possessing characteristics of both groups. Its discovery revolutionized our understanding of how one major group of animals can transform into another entirely different form of life. The Jurassic also becomes the age of true giants. Creatures so massive they challenge our understanding of what's physically possible for land animals. The impressive Diplodocus, weighing approximately 15 tons and measuring no less than 25 meters in length, moves through these ancient landscapes like a living mountain. But even the Diplodocus pales in comparison to Brachiosaurus, whose single vertebra alone measures 70 centimeters in length. This colossal creature reaches 12 meters in height and approximately twice that in total length, making it one of the most massive land animals ever to walk our planet. While dinosaurs dominate the Jurassic period with unprecedented success, the Cretaceous period continues this reign with even greater intensity and diversity. Before examining the masters of the land, let's consider their rapidly changing environment. The landscape undergoes dramatic transformation during the Cretaceous, and for compelling reasons. The first angiosperms, flowering plants, begin appearing across the world with revolutionary impact. Insects had already evolved and diversified considerably with the appearance of flies during the Jurassic. But in the Cretaceous, evolutionary changes accelerate at breathtaking speed. Pollen and nectar from flowers create entirely new ecological opportunities. This represents an incredible windfall for certain groups. Bees and butterflies experience a golden age of diversification and specialization. Mellitus fex, the probable ancestor of modern bees, becomes one of the first insects to develop specialized relationships with flowering plants like Archifructus and Mutsechia. It's now December 22nd, and young mountain ranges begin reshaping continental landscapes across the globe. For several minutes now, certain evolutionary groups have been developing with remarkable speed. New species emerge constantly, and some become subjects of intense scientific fascination, like the magnificent Triceratops. This impressive creature measures 7 meters in length and weighs approximately 8 tons of pure defensive capability. Apparently, it possessed a rather aggressive temperament. Battles between rival males must have been incredibly violent affairs, especially when competing for mating opportunities. But Triceratops, despite its formidable size, is far from the most massive dinosaur in terms of sheer weight. The trophy for heavyweight champion undoubtedly belongs to Argentinosaurus, a titanic sauropod that represents one of the largest land animals ever to exist. This colossal creature pushes the boundaries of what's physically possible for terrestrial life. Remarkable new adaptations emerge during the early hours of December 24th. Feathers, although probably present during the Jurassic, become much more common and sophisticated during the Cretaceous. We observe them in creatures like Microraptor and Sinosauropteryx, representing early experiments in what will eventually enable powered flight. It's December 25th, a Christmas day, and life is about to receive the strangest gift imaginable. The age of reptiles approaches its sudden and tragic conclusion. Major volcanic eruptions coincide with the impact of a massive asteroid that crashes into what will become Mexico's Yucatan Peninsula. The crater measures 180 kilometers in diameter. Try to imagine the absolutely catastrophic power of this cosmic collision. Earth becomes plunged into suffocating darkness, choked by dust, gas, and acid rain that turns the atmosphere into a toxic nightmare. Life quickly asphyxiates under these hellish conditions, while ongoing volcanic eruptions make the situation even more desperate. For several seconds on our cosmic calendar, animals collapse one by one across the globe. On December 26th, they all disappear in what represents one of the most dramatic chapter endings in Earth's entire story. Only the mammals, which had maintained extremely low profiles until this moment, will inherit the vacant ecological spaces left by the dinosaurs. Now we enter the final era of our planet's magnificent history. It's somewhat overwhelming to realize that this represents the period we understand best, the era when our own species, Homo sapiens, eventually makes its appearance. Yet only a few days remain before the end of our cosmic year, making our existence seem almost impossibly brief in the grand scope of Earth's timeline. Mammals gradually establish themselves across all continents and diversify extensively in ways that mirror the earlier dinosaur radiation. Some groups, like marsupials, become restricted to specific geographic zones. Primarily due to plate movements, that isolate them on land masses like Australia, where they can evolve without competition from placental mammals. In the early morning hours around 6 a.m. on our final day, the first primate makes its historic appearance. Darwinius macillae, affectionately nicknamed Ida by researchers, represents a lemur-like creature whose fossilized remains provide crucial insights into our evolutionary heritage. According to scientists who studied its remarkably preserved skeleton, this extraordinary animal serves as our oldest common ancestor. It leads not only to modern lemurs, but also to apes in the broader sense, and ultimately to human beings. You can observe its opposable thumb very clearly in fossil specimens, and it feeds on seeds, leaves, and various fruits. A few hours later, around 10:00 a.m., India completes its dramatic separation from the African continent and collides with the Eurasian plate. This collision follows the complete closure of the ancient Tethys Ocean, which disappears entirely into the subduction zone bordering the Eurasian continent. The Indian continental crust, being lighter than oceanic crust, refuses to subduct. Instead, it indents dramatically into the Eurasian continental mass. Our planet's greatest mountain range, the majestic Himalayas, emerges from this colossal collision in a process that continues reshaping the landscape today. Simultaneously, countless new animal species continue appearing with remarkable frequency. All the biological groups we recognize today gradually emerge during this time. The continents increasingly take on the familiar shapes we know from modern geography, though they're still slowly drifting toward their current positions. Seasonal patterns begin marking the rhythm of Earth's changing landscapes in ways that become increasingly recognizable to modern observers. Climate systems develop the complexity we associate with our contemporary world. Around 8:00 a.m. on December 31st, the first hominids finally make their entrance in our cosmic timeline. These early human ancestors represent the beginning of a lineage that will eventually lead to our own species. Only a few hours later, at approximately 11:50 p.m., a large-scale volcanic eruption at Mount Toba in Indonesia sends massive amounts of ash and dust into the atmosphere. This catastrophic event lasts less than 1 second on our cosmic scale, equivalent to just a few decades in real time. This volcanic winter causes the loss of almost 60,000 individuals from early human populations, creating a severe genetic bottleneck that affects our species' development and diversity. It's now 11:56 p.m., and Cro-Magnon humans, our closest prehistoric relatives, finally establish their presence on Earth. But there are only 4 precious minutes remaining to accommodate them. In our cosmic calendar, the pace of change becomes absolutely frantic as we approach the present moment. At 11:57 p.m., ice ages and interglacial periods follow one another in rapid succession. Despite harsh climatic conditions that would challenge any species, many organisms manage to survive these difficult transitions. This resilience doesn't extend to every creature, though. The woolly mammoth becomes extinct at precisely 11:58 p.m. But human populations continue proliferating and spreading across virtually every corner of the globe. We're now discussing truly modern humans, Homo sapiens, in the fullest sense of the term. Our species has developed the cognitive abilities, social structures, and technological capabilities that will eventually reshape the entire planet. It's 11:59 p.m., with just seconds remaining on our cosmic clock. We find ourselves in the Sahara Desert, observing a landscape that would be almost unrecognizable to its ancient inhabitants. You might not realize this, but this now arid region was once lush, green, and humid. Many animals, including early human populations, took full advantage of the abundant natural resources this region offered. But climatic conditions gradually shift toward dry and arid extremes. Survival becomes increasingly difficult in such harsh environments. Human populations migrate toward the fertile Nile Valley, laying the crucial foundations for what will eventually become one of history's greatest civilizations, ancient Egypt. We modern humans have existed since 4 p.m. on this cosmic day, but Cro-Magnon humans have been present for only 4 minutes. One of humanity's oldest ancient civilizations emerged merely 27 seconds ago. On our compressed timeline, the acceleration of human development during these final moments is absolutely staggering. We're now just heartbeats away from the present moment. It becomes impossible to examine our recent history in meaningful detail. Whether we're discussing human technological advancement, the evolution of contemporary fauna and flora, or Earth's ongoing geological processes. Whether we consider our planet's story in terms of vast astronomical numbers or on this compressed cosmic scale, the dimension of time remains absolutely mind-bending. Earth's incredible history represents what makes our world such an exceptional planet in the vast cosmos. But our journey doesn't end here. Earth's future timeline stretches far beyond human imagination, filled with transformations that will make everything we've witnessed seem like a gentle preview. Our planet will continue its relentless evolution. Continents will keep their eternal dance across the surface, and life will persist in adapting to ever-changing conditions. The story we've traced from cosmic dust to complex civilizations represents just the opening chapters of Earth's magnificent journey through time. The secrets we've uncovered, buried beneath our feet for billions of years, tell tales of unimaginable transformation, catastrophic upheavals, and remarkable resilience that continues to this very moment. From the hellish Hadean landscape to the explosion of Cambrian life, from devastating mass extinctions to triumphant evolutionary radiations, our planet's history reveals the dynamic, ever-changing nature of the world we call home. Every rock formation we encounter, every fossil we discover, every geological layer we examine serves as a chapter in this incredible narrative spanning unimaginable periods of time. This magnificent journey into prehistory continues unfolding around us every single day, reminding us that we're part of something infinitely larger and more wondrous than ourselves. The complete history of Earth represents not just a story of the distant past, but a foundation for understanding our present circumstances and imagining our future on this remarkable blue planet, spinning through the infinite cosmos. As we stand at this cosmic midnight, at the threshold of whatever comes next, we're witnessing just the latest chapter in an ongoing story. Earth's future holds transformations as dramatic as anything in its past. Changes that will reshape continents, alter climates, and challenge life in ways we can barely comprehend. The magnificent journey continues, and you've just experienced the most incredible adventure through time ever documented. The secrets of our planet's complete history have been revealed, showing us that we're living witnesses to the most extraordinary story ever told. The timeline ahead stretches beyond anything we've imagined so far. Looking forward into Earth's distant future, we encounter scenarios that make every catastrophe we've witnessed seem like a gentle warm-up for what's truly coming. Picture this staggering reality. In just 1,000,000 years from now, which represents merely an instant in geological terms, our planet won't appear dramatically different when viewed from space. The continents will have drifted certainly, but only by about 45 to 60 kilometers from their current positions. Our faithful sun will continue its daily journey across the sky, rising every 24 hours just as it always has. The moon will maintain its orbit around Earth roughly once every month. But beneath this deceptive stability, profound changes are already set in motion. Across our planet, irreversible geological processes are actively reshaping the landscape in ways that will become increasingly dramatic over time. The coastlines we know today will transform beyond recognition. Consider this incredible example happening right now. Off the southeast coast of Hawaii, an active submarine volcano has already risen more than 3,000 meters from the ocean floor. This underwater mountain continues growing every single year. In 1,000,000 years, a completely new island will emerge from the Pacific waters, already named Loihi by scientists who study these remarkable processes. Meanwhile, the volcanic islands we know today, including Maui, Oahu, and Kauai, will gradually shrink under the relentless assault of wind and ocean waves. It's Earth's eternal cycle of creation and destruction, building new land while simultaneously wearing away the old. When researchers examine the forces that will reshape our planet's future geography, they conclude that ocean levels represent the most active factor in changing Earth's appearance. Variations in underwater volcanic activity will take enormous periods to affect global geography, but their impacts prove absolutely profound. Depending on how much molten rock solidifies on the ocean floor, sea levels can fluctuate dramatically during periods when volcanic activity slows. When underwater rocks cool and settle, significant drops in ocean levels occur. Scientists believe this process triggered the sharp decline in sea levels just before major extinction events in Earth's past. The presence or absence of large inland seas, combined with the constant reunion and breakup of continents, creates major transformations in coastal regions worldwide. To imagine what our world might look like hundreds of millions of years from now, we must examine clues from the past to understand what lies ahead. Global tectonic processes will continue playing crucial roles in reshaping our planet's surface. Today, vast oceans separate the Americas from Eurasia, Africa, Australia, and Antarctica. But these immense land masses remain in constant motion, traveling at speeds of roughly 2 to 5 centimeters per year. That translates to approximately 1,500 kilometers of movement every 60 million years. Scientists can establish fairly precise predictions for this continental drift by studying the age of volcanic rocks scattered across the ocean floor. Material near mid-ocean ridges appears quite young, no more than a few million years old. In stark contrast, volcanic rock near continental margins and subduction zones can exceed 200 million years in age. By analyzing all this geological data about ocean floor composition, researchers can essentially rewind the tape of global tectonics over vast periods. This provides remarkable insights into how terrestrial continents have moved over the last 200 million years. Based on this information, it becomes possible to project continental plate movements 100 million years into the future. Given current trajectories of movement across our planet, it appears that all continents are heading toward another massive collision. In approximately 250 million years, most of Earth's landmass will once again merge into a giant supercontinent. However, the exact structure of this future supercontinent remains hotly debated among scientists. Taking into account current continental movements, we can predict their trajectories for the next 10 to 20 million years with reasonable confidence. The Atlantic Ocean will expand by several hundred kilometers, while the Pacific Ocean shrinks by roughly the same distance. Australia will drift northward toward South Asia, and Antarctica will move slightly away from the South Pole, also heading toward southern Asia. Africa will continue its slow northward journey across the Mediterranean Sea. In several tens of millions of years, Africa will collide with southern Europe, completely closing the Mediterranean and creating a mountain range comparable to the Himalayas at the collision site. So the world map 20 million years from now will still appear somewhat familiar to us. But when modeling a map 100 million years in the future, most researchers identify common geographical features that seem almost inevitable. Scientists agree that the Atlantic Ocean will exceed the size of the Pacific Ocean, becoming the largest water basin on Earth. According to one major theory, the Atlantic Ocean will continue expanding while the Americas eventually collide with Asia, Australia, and Antarctica. In the final stages of this supercontinent assembly, North America will close the Pacific Ocean to the east and collide with Japan. South America will rotate clockwise from the southeast, joining the equatorial portion of Antarctica. All these pieces will combine in an astonishing continental puzzle, creating a single massive continent stretching from east to west along the equator. Today, both major supercontinent theories remain popular among geologists. Whatever the outcome of this scientific discussion, everyone agrees that while Earth's geography will change significantly in 250 million years, it will still reflect patterns we can observe from the past. According to computer simulations, around 200 million years from now, average temperatures on Earth should fall slightly below 12 degrees Celsius. At the same time, global sea levels will drop by approximately 200 meters. In this configuration, conditions for complex life development will remain quite favorable at low and mid-latitudes. Only after around 400 million years will average surface temperatures fall to about 10 degrees Celsius, with ocean levels dropping more than 500 meters from their current position. In this scenario, all continents from north to south, even at moderate latitudes, will be covered by glaciers. Mountainous regions at equatorial latitudes will also become frozen wastelands. However, this cold period won't last forever. After another 200 to 300 million years, an equilibrium should establish itself between decreasing temperatures and the increasing brightness of our sun. The temporary assembly of continents around the equator will help moderate the impact of ice ages and stabilize sea level changes. Where continents collide, mountain ranges will rise dramatically. Climate and vegetation patterns will transform completely, and oxygen and carbon dioxide levels in the atmosphere will fluctuate significantly. These changes will repeat throughout Earth's remaining history, following patterns we've already observed in the geological record. But our planet faces threats from beyond as well. Within 500 to 600 million years, a gamma-ray burst or massive supernova explosion will likely occur less than 6,500 light-years from Earth. Gamma-ray bursts represent the most intense and energetic explosions in the universe, and astronomers believe they're linked to extremely powerful stellar deaths. If such an event were to occur relatively close to us on a cosmic scale, it could trigger a mass extinction. A gamma-ray burst directed toward Earth and lasting just 10 seconds could destroy at least half of our planet's protective ozone layer. Large-scale ozone depletion would have catastrophic consequences for food chains, leading to the death of countless species. A gamma-ray burst would annihilate life forms on Earth's surface and in the upper layers of our oceans, which currently supply significant amounts of oxygen to our atmosphere. Meanwhile, due to gravitational forces, our moon continues moving away from Earth. It has already drifted more than 20,000 kilometers farther from our planet since its formation. Within 600 million years, the lunar disk will no longer be able to completely cover the sun during eclipses. All future eclipses will be annular, with a ring of sunlight visible around the moon's silhouette. The fate of Earth becomes intimately linked to that of our sun, which, like all stars, cannot shine forever. Within 600 million years, our sun will undergo gradual transformation, resulting in progressive increases in both brightness and heat output. This enhanced solar energy will affect minerals present on our planet, leading to increased weathering. Increased weathering of surface rocks traps carbon dioxide in soil as carbonate compounds. As water evaporates from Earth's surface, rocks harden, leading to a slowdown in plate tectonics that eventually comes to a complete halt when oceans evaporate entirely. The first signs of trouble appear within 600 million years, but the situation becomes critical only when average temperatures reach 47 degrees Celsius. From that moment forward, Earth begins losing water progressively, fundamentally modifying its atmosphere. Our planet transforms into what scientists call a humid greenhouse due to massive evaporation of surface water. The main consequence should be the complete disappearance of Earth's oceans within approximately 1.1 billion years. Higher temperatures cause oceans to absorb more carbon dioxide, a gas absolutely essential for plant life. This absorption reduces atmospheric carbon dioxide, creating dangerous imbalances in plant life cycles. In approximately 600 million years, atmospheric carbon dioxide levels will fall below those needed to maintain photosynthesis in most plants. When levels fall below critical thresholds, complex plants begin dying en masse, leading to dramatic reductions in oxygen production. This massive disappearance of plant life will have absolutely devastating consequences for all living beings. Plants form the foundation of virtually every food chain. Their decline means drastically reduced food resources for plant-eating creatures, which suffer severe population declines as ecosystem balance collapses entirely. Large warm-blooded animals such as mammals and birds will probably disappear first due to their higher oxygen requirements. As atmospheric oxygen levels fall and temperatures rise relentlessly, complex life becomes increasingly impossible. Cold-blooded vertebrates such as fish, amphibians, and reptiles could survive longer than warm-blooded animals in this scenario. They possess better heat tolerance and generally require less oxygen for survival. Invertebrates could represent the last animals surviving on Earth before all animal species finally disappear. Some insects can survive temperatures reaching 56 degrees Celsius. In general, terrestrial life will initially prove more vulnerable than marine life due to water's temperature regulating effects. Depending on oxygen's persistence in the atmosphere, animal life could continue for up to 100 million years after plant disappearance. Some bacteria and microorganisms could survive even longer, persisting until the atmosphere becomes too depleted to allow any form of photosynthesis. As a result of these interconnected processes, multicellular life forms could become extinct within approximately 800 million years. Complex organisms might disappear within 1.3 billion years, leaving only simple bacteria to face an increasingly hostile world. But the sun's story continues far beyond this point. In 5 billion years, our sun will leave its main sequence phase and begin transforming into a red giant. Having exhausted hydrogen reserves in its core, the delicate balance that has maintained solar stability will collapse. Our sun will swell to colossal proportions, reaching diameters exceeding 100 million kilometers, nearly 100 times its current size. It will become thousands of times brighter than today, transforming into a pulsating red giant that fundamentally alters conditions throughout the solar system. Mercury will be swallowed and vaporized. Venus might escape by the narrowest of margins. Earth's fate remains uncertain, but conditions will become absolutely hellish regardless. Average temperatures will reach several thousand degrees, turning our planet's surface into an ocean of molten lava. Most of Earth's atmosphere will escape into space. Any remaining solid surface will be transformed beyond recognition, with floating continents of metals and metal oxides drifting on seas of molten rock. Eventually, even this red giant phase ends. Our sun will shed its outer layers, scattering them across the cosmos. All that remains will be a dense ball of carbon and oxygen known as a white dwarf. It will continue glowing for several billion more years before gradually cooling to become a cold, dark sphere. In 9 billion years, our sun will be dead, its nuclear fires extinguished forever. Any remaining planets will become dark, icy worlds orbiting a stellar corpse. They'll continue their eternal dance around their dead star at reduced speeds due to increased distance and diminished gravity. More than 4 billion years later, even the white dwarf sun will have cooled to insignificance. Its radiation will become so weak it drowns in the cosmic microwave background. Our sun will have transformed from white dwarf to black dwarf, invisible to any hypothetical observers. This represents the ultimate conclusion of our solar system's story. The prospects for planetary destruction aren't merely speculative, but based on solid scientific predictions derived from our current understanding of stellar evolution and planetary dynamics. Although we possess knowledge of Earth's distant future, it remains our responsibility to shape the immediate future. This perspective raises fundamental questions about life's future on our planet and our responsibility as a species aware of this cosmic destiny. Understanding these phenomena enables us to better appreciate the importance of preserving our environment and exploring new approaches to ensure sustainable futures for as long as possible. This represents the ultimate aspiration of a scientifically literate society and our only hope of extending the story of life on Earth. Our magnificent journey through Earth's complete history, from cosmic dust to the distant future, reveals a planet of extraordinary resilience, constant transformation, and ultimate impermanence. The story continues unfolding around us every day, reminding us that we're part of something infinitely larger and more wondrous than ourselves. The secrets buried beneath our feet have revealed themselves across this incredible timeline, showing us that Earth's story represents the most magnificent adventure ever documented. From hellish beginnings to the emergence of consciousness itself, our planet's biography serves as a testament to the power of time, change, and life's remarkable ability to persist against overwhelming odds. This has been the complete history of Earth, a magnificent journey into prehistory that reveals our place in the cosmic story. We are the universe becoming aware of itself, living witnesses to the most extraordinary tale ever told. The adventure continues, and you've just experienced every chapter of the greatest story in existence. Our planet's past is a tale of chaos and creation, extinction and emergence. Understanding this ancient story connects us to the deeper rhythms of nature. If this journey inspired you, don't forget to like, share, and subscribe for more awe-inspiring explorations into Earth's untold stories. Stay curious. Adventure awaits.